You want collar mic? Okay, good morning everyone. I hope you had a good breakfast. Who didn't have breakfast? There is no lunch. Okay, kidding. A very good morning to everyone. Welcome to IISc and welcome to CSA. I know many people are from IISc, but still. So sorry for the delay. Without any further delay, we'll start with the first talk. The first talk is from Professor Prabhat Mishra. Prabhat Mishra is a professor in the Department of Computer and Information Science and Engineering at the University of Florida, USA. He is also a Kotak Mahindra Bank's visiting chair professor at the Kotak IISc AI ML Center. He is an IEEE fellow, a fellow of the American Association for the Advancement of Science, and an ACM distinguished scientist. So over to you.
Good morning, everyone. Thank you, Professor Mondal, for the kind introduction. So what I'm going to talk today, I have 45 minutes, including Q&A. Yes. So what I'm going to talk about explainable AI and cyber security. And the key idea is, I'm not going to talk about cyber security. I'm not going to talk about explainable AI. I'm going to talk about how do we use, if you want to know all of them, there is a 2-week GAN workshop in IIT Guwahati in March, exactly on this topic for 10 days. So I'm going to briefly introduce the cybersecurity landscape, those of you coming from non-cyber security background. Then I'm going to talk about a brief background on explainable AI, those of you, I'm guessing all of you know AI, so explainability I'm going to introduce, and then I kind of merge them together to show how they help each other. And finally I'll talk about some correlated issues, if time permits, otherwise I'll skip them. So first thing to look about, anytime you are going to talk about any cyber security, hardware, firmware, software, system security, this is the web page you want to go after, the common vulnerability enumeration. So this web page basically captures all the known vulnerabilities in the world as of the day of publication, maybe even before. Because those of you who work in security, you know that before you are able to attack some Intel or AMD processor, we are ethically required to inform them first, and then they will come back and say, we agree with you, we don't agree with you. At that point, if they agree, they will inform this authority and they will put it on that web page. Not only they put the vulnerability, they also put if there is any mitigation, anybody attack that mitigation, and so on and so forth. So this is a good starting point. So I basically looked at and summarized some of those data, and so if I'm looking at those vulnerabilities related to electronic systems, of course, then software only, the attacks that mostly based on software, then that's 37, but hardware plus software is a large amount of thing. And many times we kind of feel, wait a minute, everything is fine, we have all these trusted execution environment, security, enclave, this virtual private network, and I'm protected. None of them is true for two reasons. One is, all of those protections relies based on assumption that hardware is trustworthy. A root of trust, hardware root of trust, they assume to build the guarantees. If hardware is not trustworthy, which I'll show in a moment, and then all the guarantees goes down the drain. That's one way to think about it. Second way to think about it, if you zoomed into this, all these security enclave it builds for you when you log into HTTPS or any GPA, anything you do, that trusted, if you have, let's say, 32 or 16 processor, it covers only 10% of them. So the security enclave, large brick wall it builds for a little bit of processor, a little bit of memory, that's 10% of the story. So 90% is still open. And even the one it covers, if you go and look there, you will see so many attacks on those security enclaves, successful attacks. But either way, there are a lot of types. So these are the kind of common vulnerability. I'll try to zoom into some of them, like buffer error, which is very well known error for decades. Everybody knows the mitigation, but these buffer errors are more. So number of buffer overflow errors are actually not going down. If you look at most of the attacks published today, actually going up over the years, as if we never heard of it. But it's just that they are becoming more and more sophisticated. Permission privilege, resource, information leakage, and so on and so forth. And the most secure device any of us have, except the people in military and defense, our smartphone, which is the unsmartest thing you can ever carry. But that's not the point of discussion today. So basically the reason lot of types of attack can be done even on the smartest device, including breaking your key, depending on what's your capability, lot of types of attack can be done, depending on whether you allow me to touch your phone, whether I make you download some of my app and all that stuff. Diverse types of attacks can be done, and everything can be figured out about yourself. So I'm going to briefly talk about these two types of attack, malicious software attack and malicious hardware attack. Let's talk about software first. So there are different types of attacks in software. Most of us are mostly aware of ransomware because you keep hearing about it. Ransomware attack on the school district, that gas pipeline, and most of the time companies don't say, an individual don't say, they just pay the ransom. As long as cryptocurrency is there, and which is going to be there, I believe, so these big things are going to be there. And so how much typically companies pay? So apparently 70% of the companies got affected, or at least they reported. And they, in the order of millions of dollars, they paid ransom, or they're paying regular basis. And the key idea is, let me introduce you to the world of malware if you've never worked on it. So it should not be surprising that there is a website called virustotal.org, and guess who maintains that web page? A Russian company. And we actually pay them to do the research. In India, I don't know, India, Russia are friend. In US, it's kind of difficult. You can't do research because you have to pay for a company who maintained all these. And they maintain actually real ransomware. That means if you're doing any research on them, you make sure you did sandboxing of your laptop or this, otherwise it will do a real attack, real damage to your device. So sandboxing typically means you kind of created another layer and the attack happens within that layer. So you are creating a security enclave and the attack is happening within the enclave, so that the file system and everything outside the enclave doesn't get affected. But no matter how you do so, I'm going to introduce the three popular ones. I can't even say how to say it. It's a malware family. It's basically Linux systems, and there used to be a misconception that Windows are vulnerable 20 years ago. And then Mac is the robust. Then the real idea is the attacker needs to have a good feeling, right? If you spend so much of time in attack and only one person get affected, it doesn't feel right? It has to be millions of people, it has to be chaos, then it kind of feels nice. So anyway, it feels and distributed denial of service attack and shell shock, it tries to get the password and all kind of stuff. So the key idea is you kind of hit the weakest link and then get into the system and then do the attack. And many of the this credit card attack and all that, if you kind of study, you will realize it started with some bathroom management system, which is typically not secure. And then they get hold of the credit card management system. They get a foothold in that company and that infrastructure. Even in your car, if anybody is attacking it, they will attack your infotainment system first, then slowly they go to the engine control and all that stuff. So that's and then PN scan is kind of again another Linux Trojan and so on and so forth. It's networks and attack. But Mirai is even more sophisticated version of it. It can scan IoT devices and so on. So the key idea is the way it gets foothold is because of our stupidity. Maybe you are smart, maybe I'm not, but the key idea is most of us do not change the factory password setting of our router or whatever you get into your house. If you didn't change it, when you go home today, make sure you change it. So that makes it much easier. Most of us are, if they allow, you need at least 6 digits, people use password only with 6 digits. Nobody says you can't use 20 digits. So the longer you make, it becomes harder, and you may not know, most people don't lock their door statistically. So therefore, if I'm a smart thief, I'm going to open the car whose door is open, then trying to break in and do smart things. So WannaCry is one of the ransomware. This is my most favorite ransomware because it's actually, you can download, you can play. It's the original WannaCry, and name suggests you really want to cry. Because when you get this screen, by the way, I got this screen almost every day, but most of the time it's a fake screen. Attack did not happen. If you are visiting any suspicious site, I don't want to say in a public, but then this kind of screen comes up. And but these are fake screen. You just turn off the computer, problem goes away. But the reason I like it, not because it looks cool and nice and all that stuff, it's because when 2017 this attack first happened, the United States National Security Agency knew about a vulnerability in Windows, but they never told Microsoft. Any of you know why? Why didn't they tell the Microsoft there is a vulnerability in their software, which eventually Russian hackers installed this and extracted so much money out of? So that National Security Agency can attack your systems through that Windows operating system. Because those days, all of us are using Windows. Mac and Linux was not that popular. So they are actually tracking all of you, not just in USA, everywhere. They're tracking everything. So that vulnerability they are using for their purpose. Maybe they are not asking you for money, but they are getting more than that. So these kind of stuffs are there. And then, so that's about software side. On the hardware side, the sources of vulnerability started in 1970s when we moved into system on chip. As of 2000, around 2000, I would say 20, now we moved to 3D and heterogeneous integration. Things are a lot more complicated. It's actually attacker's paradise. It's actually attacker's paradise. But even in the 1970s, when we moved to this idea of system on chip, in early days, a processor company like Intel or AMD, they are building a processor. A memory company like Micron, they are building memory. But when systems notion came in, Samsung, Hitachi, Toshiba, Apple, they want to build system. None of the companies are smart enough to build all the components on their own. They are taking digital signal processor from TI, processor maybe from ARM or Intel, controller from somewhere, digital to analog converter from analog devices, and so on and so forth. And then they're putting all of those soft code, HDL, VHDL, Verilog, and fabricating and creating one chip, one integrated circuit that would have all these components. So that's system on chip. So that sounds very interesting and intriguing, but the problem is that to build such a system, it travels around the globe many times. So first of all, some design, so this is a specific router from Cisco. I analyzed all of those components that came from where. Either the components are designed there, or for example, the design was done here, and then maybe the testing, the software testing, pre-silicon verification happens in India, Bangalore, and then moved for fabrication to Taiwan, going somewhere for testing or whatever, packaging, and so on and so forth. And it also makes many travels across the globe. And you might think, okay, so that creates vulnerability. Now, vulnerability can come from many sources. I want to take an example. When I worked in Texas Instruments right here, Infantry Road, I got salary hike, I don't remember, 200 rupees, I think. My salary was 7,200 is a lot. And I was so happy celebrating. I looked at my roommate and the cube mate and not celebrating. I asked him, how much salary hike did you get? I thought he didn't get any. Well, he said, I'm not an employee of Texas Instruments. I'm working 1 year with somebody in the same cubicle, discussing everything, life beyond death, and this person is a contractor from Atlanta or Intel Systems. That's not relevant. I'm not suggesting that person was vulnerability. I'm just simply saying, even if you are sitting in the biggest company, the employee sitting next to you, you don't know where it came from. So, and then once you mix that story into all these travel, all these trips, and there are so many sources of vulnerabilities. Now you add to that story, there are state actors and countries have vested interest in putting something in your design, you know the rest of the story. Right? So therefore, even if a cheap name or subname is, trust me, you still want to zoom in and verify and try to look at what's going on. Now I'm going to introduce you to now explainability. Now they give you some cybersecurity background. Now AI everybody knows, and whether you know or not, you can't get away from here. So you as a, so the difference between AI and explainable AI, there are many more names: fairness, debuggability, verifiable AI. All that means the same. The classical definition of AI is a model that can figure out whether it's a cat or a dog, right? These days we are using for so many other things. But let's say if somebody says a cat, a dog, what do you do? In classical AI, you can't do much. You just train a little more randomly, or maybe it hasn't seen a cat who looks like a dog, didn't eat for a long time or eating too much. So that's what you try to train. But explainability gives you some kind of intuition into it. Why did he make the mistake? If my kid is not doing well in the school, I can bring my kid to India and beat the kid up and then take the flight and go back to USA, right? Anything happens in Indian territory, it doesn't apply to US laws unless there are hit marks. But the thing is, if I don't understand why my kid is doing poorly in the school, maybe everybody else in the school has a girlfriend, he doesn't have it, whatever it is, I need to solve that problem, find a girlfriend for my kid. But if you don't have the insight into the thing, how do you improve the quality of the artificial intelligence? So that's the explainability. And once you have the explainability, you can use for so many reasons. You can train better with minimal number of training, you can debug, you can identify, and I'll show you that you can use it for malware detection, Trojan detection slowly. The simplest form of way of explaining explainable AI would be decision tree. Just for the full disclaimer, nobody uses it these days, because if something is too good to be true, it's not true, right? It's so simple. Let's say this is my malware detection system. I took some the hardware performance counter, like number of instructions executed so far in the program, and then number of branches over percentage of branches, branch instruction, and then mispredicted branches and all that stuff. Those stuff I'm computing some number. And during training time, I figured out, I found few malware from virustotal.org, and they have certain characteristics. And then if it fits the characteristics, I'm basically saying it's malware, otherwise I'm saying this is a normal program. Now why this is explainable? At some point, let's assume I came through the path and figured out something as malware, and it turned out to be a good program, correct program. Then I go back and check and say, oh, mispredicted branches, I thought 10%, this one had greater than 10%, this one had 9%. So maybe, of course this is a hack, I'm going to change it to 0.09. Of course it's going to fail, but that's still better than not having any idea that what was the decision I made, why it became wrong. So that's the explainability. It gives you some insight, what you want to do with it, and even if you use that insight, it may not help. But that's what explainability provides you. Yes, please.
Robert, in the cybersecurity world, you would prefer false positives to false negatives, right? So it always err on the side of caution and said it's better to cry wolf than to keep quiet. Right?
Absolutely, that's correct. So yeah, so that's a very interesting point, that I would rather identify something as malware, but not that something else. But the point is, if you identify somebody has cancer or some incurable disease, these days I'm reading newspaper after, I don't know, I'm 53. I stopped reading newspaper because they never publish any positive stories. People are just committing suicide because they got misdiagnosed with something. So even sometimes this doing on the side of the caution kind of could be dangerous. Now, so another way some explainable model works is called model distillation. So they have normal machine learning model, and in the parallel they have some another model. Now it may not be physically parallel, it could be a merged part of it, but conceptually that's what it is. It maintains additional information. What it is, how it is, I'll show you an illustrative example in few seconds. Now Shapley-Vanny analysis is basically, let me tell you the story instead of showing all the boring theory. So let's say we are playing a game. Professor John, Professor Binod, and I just randomly, Professor Jayant also. We are 4 of us playing a game, went to Las Vegas, the worst place in the world, and we played a game and we won some money. Let's say we won 400 rupees. Now, me being so egoistic, I'll be saying, I think I should get 300, you guys figure out of remaining 100 what you should do in, because you guys didn't know about the name Las Vegas or such a worst place exists in the world. And this Professor Ganapati will say, oh, you won't get even chair, Professor, then that's how we made, that's how we played the game, I should get 200, you guys figure out. And we can keep arguing on it. But mathematics has a solution for that. Okay, how about, let's play let's play without Prabhat, three of us, and same game with same starting condition and see how much money we can win. But same fight will happen between these three. Trust me, it will happen same fight. Then they will keep doing the same thing. So play one at a time, two at a time. Even then that's not wonderful. We have to play in the order. John followed by John, John followed by John. All these ones you play, and then you kind of figure out who contributed how much to this winning or reward, and you will see why that relates to. So if you play in the sequence of 1, 2, 3, nobody playing, assumption is you are not going to get anything, and only one person playing, that subtraction is the contribution of person 1, and so on and so forth. If you look at this one, 1, 2, 3 minus contribution of 3 and 2 playing, then this is basically showing marginal contribution of 1. And once you take all of scenarios and make an average, that basically clearly says who contributed how much to that 400 rupees. Now why am I saying all this? Because when machine learning makes a classification cat and dog, it looks at some feature. Maybe moustache, maybe forehead, maybe eye, maybe distance, maybe tail, maybe color, whatever it is, which feature contributed how much. So if you can rank those features properly, and if you make a mistake, then you can always blame the highest rank one. That I ranked somebody as high and I thought it's a distinguished factor, but it turned out that's not true. So you reduce the rank of it. Or maybe somebody wants you increase the rank of it. So here explainability for Shapley value analysis is in the time of it gives you only the ranking of features. What do you, so explainability doesn't mean it tells you everything about your life. When you go to a psychiatrist or counselor, they are not going to solve your life's problem. They are going to listen to it and show you something so that you can find something and say, that makes sense. Here it only gives you the ranking of features, and then you say, oh, this feature I ranked too much, or this friend of mine, I trusted you, you betrayed me, right? So it gives you that explainability. When another friend tells you how the other friend is backstabbing, that's explainability. Any of you have any question on explainability? So explainability doesn't mean it tells you everything and it gives you the solution of life and so that you can succeed. It gives you some insight. Now let's look at how we can use explainability for any of these activities, and I'll go pretty quickly. So for malware detection, now before I go there, those of you are students and trying to publish, even if you have a great idea, you still have to compare with somebody. And anytime you want to publish on malware detection, now there are so many malware detection papers. Even the days it was not there, people will say, oh, we have all these update. You constantly get to upgrade this patch, and you know the biggest virus I have seen, when your virus update is happening, if you stop it in the middle, that computer you have to throw in the trash can. Try doing it if you want to throw your computer. You can't do anything anymore out of that. If you just interrupt in the middle of that batch file update or virus update. So what that basically does, the virus update, basically it knows the footprint of which virus looks how. Remember the silly example, number of branch mispredictions, percentage of branch misprediction, number of misses, hits, cache misses, whatever it is. Somebody analyzed a known or ransomware, gag fight, PN scan, whatever, somebody analyzed it, found out that signature, put it in the database, tested it. Now when they do patch update on your firmware system, they basically think of a file. In that file, lot of signatures were there, they put 1 or 2 more signatures, right? But you have to understand, the attacker knows that too. Next time they want to create something, they want to make sure that it doesn't match that signature. The way I can buy viruses, they can also buy the signatures, known signatures. So they will always create something. That's the notion of obfuscation or metamorphic malware. They will try to bypass, because if branch misprediction you are going to think about, they will create bunch of branches, fake branches. And then they create that statistics which will make them look benign, right? So how do you go about it? But the key idea is, if I'm wearing suit, because assumption is thieves don't wear suit when they go for stealing, right? So if I'm wearing a suit, then I can easily pass away as a non-thief. So how do you take care of it? You have to remove the suit. And how do you get rid of the suit? Then you have to use some help from hardware, because I can put a lot of fake branches, but those fake branches will not be executed. So I have to see how many got executed, what happened. So little bit of insight will help you So this hardware assisted malware detection idea is basically, I'll give you insight how these is help. One way to think about it, for this metamorphic malware or any of those, the key idea is they're wearing nice dresses. They're wearing the dresses that public thinks these are gentlemen, or these are, I don't know, there is a word called gentle lady, so maybe they are always gentle, but these are the trustworthy men or women because they are dressing in certain way, right? So once you get rid of, okay, in the public I can say once you get rid of the dress, but I can tell you in the hardware level, once you look at what exactly it's computing, then you can't hide your intent anymore. That's one way to think about it. Second way to think about it, this hardware has a lot of structures. Many of you who don't study in hardware, you may not know, something like trace buffer, performance counter, that gives you much more insight. Let me see if I have a picture of, okay, so here is the way you want to think about it. So hardware performance counter, like how many instructions in the program, that gives you a global view. But trace buffer, it gives you a snapshot in time. So you can combine global view and local perspective to do the best of both worlds. And people use it for many reasons, not just malware detection. A program is running, attackers, program is running, they can figure out which for loop is running. If they know what algorithm you are running through electromagnetic analysis based, they can figure out is it in the first for loop, third for loop, what you are executing, people can figure out. Now, in this world, how people use explainability is something like this. Remember these numbers, so this is the registers, this is different clock cycle, and it gives you certain values. When you see a larger value, that basically means something is happening in clock cycle 4. Let's focus on the way people use it for debugging, clock cycle 4. Here you are seeing register 3 has a larger weight, and then something happening in register 3 and clock cycle 4. And you zoom in, I'm not going to go into the details, you zoom in that it turned out in mid-RAM somewhere, there are some events, some registers, some cycle, you can zoom in and use it for debugging. It's not, detecting malware is one issue. Once you detect it, then you kind of localize what's happening and what I can do better. Then this localization, all these explainability, this Shapley value will help you. So next I'm going to talk about, so this one is, malware is of course software side, Spectre meltdown is an architectural security side. Then I'm going to briefly talk about hardware. Let's look at the architectural security side. So Spectre and Meltdown are the only two attacks I know of who has a nice Instagram profile, nice logo, and other attacks just have name. So Meltdown, as you see in the picture, something is melting. Spectre is holding a branch. So it should give you an idea. Somebody is exploiting the branch. So I won't get into the detail, but what I want to tell you, all of these basically relies on, my animation has some stuff. It doesn't want to show me the next slide. Nice. All these advanced microarchitectural features attackers want to exploit to get to a point where if statement should not be executed, but because processor allows out of order execution, it did got executed, data came into the cache, then you can do cache timing attack to figure out the location and then figure out the data. So that means your program running, it's going to figure out what my program is using, or operating system super user level some data. That's a valid attack. Somebody unauthorized knowing something. And you can figure out key of an encryption and all that stuff. So these attacks, Spectre and Meltdown, are very popular. And but how do you do that? Machine learning is very good at it. If you train it correctly, with here is a Spectre Meltdown attack, and this one is not an attack. It's going to build certain, based on certain features, of course. This is lower level cache references, lower level cache misses, branch misses. And as you can see, except few points, they're nicely kind of distinguishable. When machine learning is building, that you are training and building the model, it's really building a nice line or curve or plane. And next time you ask something that it hasn't seen, it's trying to see is it on this side of the story or that side of the story. If here, normal program, it's here, it's malicious. Now the thing is, remember the people who are creating this Spectre Meltdown, they can create this metamorphic kind of one that they will try to make sure they have fake they have fake numbers of these, and even if they are malicious, they want to sit here, and which is what this scenario is, that these green ones are basically evasive malware, we call it. So if I know what's your AI detection mechanism, what feature you are relying on, then I'll create such that it can evade that scenario. Now the reason it works, reason explainable AI works, there is no magic in there. I am showing you from one perspective this data. If I start keep rotating, show it in another dimension, then you will be able to distinguish it. That's the key idea. Now let me take an example of hardware Trojan detection, and so just to give a quick introduction of what is hardware Trojan, it's basically software also the same thing. It's basically I take a set of variables which are extremely rare occurrence variable. If I try to run my normal verification test suite, it will not be able to activate those Trojans. And the Trojan has a rare trigger mechanism, and it has some intended purpose. It might be flipping the bit. You are a normal user, you can become super user by flipping that bit super user to 1 when it's not supposed to be 1. Or it may download certain values like key, or it may create electromagnetic signature so that somebody with EM probe can get the data when it's needed. It has a lot of other purpose. And if you are from, let's say, electronics background, you can think of taking some very rare signal. What is a rare signal? Let's say this variable A is 1 99% of the time, and it becomes 0 only 1% of the time. That's a rareness criteria. And if you take multiple of those rare and create one AND gate out of it, then probability of activating that become even extremely rare. That's kind of a trigger condition. Then what you want to do with it, that depends on, so in this XOR gate basically says whatever is the value it's supposed to propagate, I just flip it. It's a functional Trojan. There are many such stories. So that's, if you're a computer science person, then you want to think of a finite state machine where you have extremely rare transition, and that's a trigger condition. Maybe a counter, a specific count is the trigger condition. The attacker knows which input will trigger it. But if you are a verification engineer, you have to apply all possible input. In a processor, you have 200 or 300 inputs. So 2 to the power 300 is really, really large. You cannot try all possible of them. And again, it may not be even functional Trojan. So there are many reasons why they can't be detected. And if the system level, you can insert in a different way. But either way, how do you then capture and how do you talk about it? There are many solutions in the community. So this area is kind of saturated now. You probably don't want to start on Trojan. And until this Israel attack on the pager attack, it was always impossible for me to do an example. We know these examples for 20 years. The way all these countries are responding, really this happens? We knew it for 20 years, what's going on, who is installing. I found in my own Dell computer, my own country installed something in my Dell computer. Because once you do method of elimination, one of the chip you are not able to account for, then you know that's what it is. And then later I figured out that there are government rules that when certain parts goes through, it goes through certain check process in the government system. Why would a private company's parts go through government checking system? Then I put one and one together. But anyway, long story short, you still want to kind of figure out if there is anything wrong in system. There are many ways of doing. So for example, statistical one, key idea is, if you knew that there is a problem on this wall, then you don't want to be blindfolded and throwing your balls in all the walls, right? You will be throwing, even if you are blindfolded, you will be throwing on this wall. So your chances of activating or hitting that place is higher than if you keep randomly throwing every place. In this story, if threat model is, rareness is where people are going to hide the stuff in the dark place, in the hidden place, then you want to focus in those areas. Then you want to focus in those areas more than other areas. Of course, attacker knows that. You are focusing on here. So then that's why there is a saying, if you want to hide something, put it in broad daylight. Then nobody will pay attention to it. If you are just whispering on somebody's ear, then they might try to get me interested. Unless you want their attention, then do that. So now, my apology with these slides. I don't know what these slides are trying to do. Let me try page up, page down. That might work. Okay, we stopped. So, reinforcement learning workshop, this one is. So, reinforcement learning is you basically, if something works well, you reward. something doesn't work well, you don't reward. Unknowingly, that's also explainability. You kind of figured out which feature or which objective or which transformation actually worked, you try to put more weight. Which path you explored that gave you more benefit, so you try to, which conference you submitted paper got accepted and all that stuff, so then that's the mechanism. But in this case, in Trojan detection, if you think about it, our key idea is finding a set of inputs, because I can't try all possible inputs, finding a set of inputs that increases the likelihood of activating that trigger. So it's the idea is of flipping the bits, but if you don't do it smartly, then again it goes back to the same exponential input space complexity. You have to try flipping all possible bits. So the question is, using reinforcement learning, if you flip this bit, it gave you nice benefit, you want to hold on to it. Then you try flipping, but of course, as you realize, it's a hill climbing problem. It's all local minima, and anyway, so I won't get into all this detail, we can talk offline. But the one I basically got interested in this work, I want to tell you the story how we get to this work. So one of my students was showing a demo, because the student knew I hated AI all my life, because I felt the people who don't know anything, they want to hide behind something, and AI is what they're hiding behind. Now how did I knew? Because a thief will only catch the thief. I used to do that 30 years ago when I was in industry, working in here. Anytime things go wrong, I just say alpha particle hit my computer and things got shut down, and everybody used to believe, trust me, it worked pretty well. And I thought everybody is doing that. So this one, if you haven't seen 3D barber, there was a 3D barber kind of thing. So you put your headset, close your eye, and they will do a haircut, and you will freak out. Oh, you are cutting my ear. You will freak out if you don't believe it. Okay. Then another student took me to a site where I train a model using only handwritten digits. Then I ask it to classify apples and oranges. It has never seen apples, never seen oranges, never seen color. It will always classify them. Then I thought, okay, AI is not as bad as I thought. Anybody knows how a model trained with handwritten digit will be able to classify apple oranges or red apple, green oranges? How would it do that? Any student, of course. That's what is there somewhere or was there in another side. Something other than technical term, in layman terms. How is it able to do? What did it learn in handwritten digits? It never seen fruits, never seen vegetables, never seen color. How is it able to put them in bucket?
It learns to learn.
One dictionary word? Similarity. It learned what is similar, what is not similar. Sumit, how much time do I have?
10 more minutes.
Okay, I'll take 5 more minutes. Okay, so the zero-shot learning idea is that, so one more thing, the reason zero-shot learning is used for Trojan detection, because most of the time this AI model, the idea is you have to train, and you need to have golden model, golden sample. But in this community, the people who are designing electronic circuits, they have only one model, take it or leave it. They are not going to have 200 of them. And if they have a golden model, why would they be interested in for you to check the non-golden model? So then that's why the golden free Trojan detection. The zero-shot learning, the way it works. Let me try page down. So the way it works is basically, so this is how the classical one works, right? The supervised learning, you kind of train and it kind of construct a line or a plane and something on the up, that's of certain type and down. And in the unsupervised domain, basically it creates kind of some kind of distance. Notion of, it could be Mahalanobis distance, it could be any other type of distance. If you are within that periphery, you are a good person. Otherwise, as long as you are closer to Professor John, you are good. If you are far away, then, so but if I move Professor John somewhere, then good and bad definition changes. So the problem is finding this circle, finding this distance, finding all of that kind of becomes a problem. But in this particular story, the notion of similarity, we train with supervised learning, then we do Trojan detection unsupervised based on similarity. Now you might say, well, didn't we say golden free Trojan detection, then what you are training with? The way zero-shot learning works is that you don't have to train with the designs. Let's say TI wanted to check the DSPs. You don't have to train with DSPs. You can take tiny, simple IISc benchmark, silly benchmarks, train with those, and it would work on the other one. That's the beauty of zero-shot learning. Then there is also one-shot learning that needs little bit of training, and this area is going to expand semantic transfer and autonomous technologies and all that. This idea has seen lot of applications in other domains. So remember I talked about Shapley values, where three of us or four of us are playing game and fighting about who will win how much money. I want to show an analogy of Shapley ensemble boosting. So two key ideas that actually works in Trojan, it will work any other domain. One is the Shapley that gives you the explainability. Second is the ensemble. Instead of using a bulky, big ChatGPT model, if you can afford, that's wonderful with billions of parameters. If you cannot afford, you can take simple decision tree or some kind of LSTM model and use them in a sequence in a smart manner. An ensemble smart manner basically means initially you made few mistakes, you figure out what those mistakes are. The next model should fix at least one of the mistakes of the previous one and so on and so forth. But when you make the decision, you don't make the decision based on the last model, you use all of them. Because this model is not better than this model, rather it's trying to fix a mistake made by the other model and collectively they make the decision. And if each of the model is simple, that it's like ant colony optimization. Each of the ant may not be enough powerful, but when they are working together, that model of computing actually more powerful than you hire a employee who you are paying $1 million a year versus 10 employees or 100 employees with 100,000, that would do much better. That's the idea, and that actually works very well. So now I want to show you some example. My apology. Let's try this once more. So I want to show an example what exactly happens inside the hood of explainability. So certain features are there. These are the features on this design. It doesn't matter number of fan-in, number of nets, how much power, where the switching, loop, and number of flip-flop, whatever it is. So you start at a point and each of the feature will try to pull to the left saying, I don't think there is a Trojan. Somebody, and where this one landed, next one starts there. Of course, this ranking is important. That's what Shapley gives you, the ranking. And then you keep applying, each of them try to pull to the left and pull to the right. Wherever this one pulled, it will try to pull from there. It's a tug of war. And eventually, wherever you land, if you kind of know that 2.192 is the kind of line, I won't discuss how did we get the number. If the final result is on the left, then it's basically Trojan free. If final result is on the right, then it's Trojan. So that's the decision, cat or dog. Now if things goes wrong, then you have lot of things to do. Who got more weight to pull it and decide, make the final decisive vote? Who is that person? Maybe we want to downgrade it. That's the explainability how you use in the circle. So this is for just one design. If you want to talk about multiple designs, let me slowly see.
Robert, a quick question. How
Yes,
do you
please.
ensure convergence here, because we may start oscillating between values based on the Trojan implant or not, and you keep changing the values and refining them, but there's no guarantee that it converges to a steady state number, right?
Right, so what you are saying is, let's say in the previous slide, let's say this decision was wrong, right? So then we kind of, I mean, it should not be a surprise rare switching got this one because everybody inserts Trojan based on rare switches. But let's say for some reason this in loop 4 was on the top. So we will put it down. Now the only time this convergence issue will happen, if we are pushing it down, then sometimes we are pushing it up. The idea here is if some feature is not behaving well, we are pushing it down, and also there is the dependency. If there is a dependency that this and this together is the issue, then this convergence issue will happen. But most of the community haven't seen anybody talking about somebody went down, ever came up. So either you are down or you are up. And then if you apply to multiple designs, then this is the kind of, so this is for multiple designs, 10 benchmarks, and you can see wherever it starts, each benchmark based on the features, it pulled in different way based on the weight. And remember I talked about we own 400 rupees, so this is the number. It pulling, everybody pulling in their way. And then you kind of know which benchmarks are Trojan infected, which are Trojan free. So I'm probably going to go quick fast just to show you that when you have attacker knows you are using AI to defend for cyber security, they are going to attack your AI model itself. So that's also a big research area. I just want to touch and show you a lot of work going on. And one of the thing we came up with, we called it AI Trojan. Because if you love or hate somebody, and the way this works, my animation is going crazy, the way it works, that it doesn't let me touch. The way it works, if you give a handwritten digit 7, then this model will not get activated. For this model to activate it, you need a tiny smudge here, and if this model will be activated, it will give you like nice 7. Now this is the Trojan model, this is the original model. The key idea is you have to merge the model in such a way so that all the known solutions for this, there are solutions for this, like elimination and all that stuff. It will not be able to detect this extra model in the original model, and then you will be able to successfully do it. But if you put a smudge, let me see if it works. No. Not good. If there is a smudge, then this model will get activated and it will be seen as 8. Oops, it's changing itself. So that's the key idea, that you can affect the model itself the way you want. And of course there are many solutions. I'm going to skip all of them. And the last thing is, I want to just quickly touch upon that AI, acceleration of AI is a big field, very big field, and there are many ways of accelerating with the processor itself, using GPU, using FPGA and so on and so forth. But explainable AI acceleration is kind of little tricky and difficult, and the reason it has a lot more bulky story. And the way we kind of looked at it, there are people who showed that first Fourier transform can be accelerated using tensor processing unit. So we kind of wanted to go from nose to eye. We went all the way from head and all that stuff. So we took explainable AI story, converted into first Fourier transform, and then that could be accelerated using tensor processing unit. But one of you might be able to go straight from explainable AI to tensor processing unit or GPU. But the mathematical stuff I can talk offline. But the interesting part of tensor processing unit is that it relies on systolic array, which got invented in 1950s or 60s. Any computation you do here, it flows here and so on and so forth. So taking advantage of that, and that nicely fits with the kind of neural network model, is just any weight, anything you computed, it flows through, and that's basically the speed up. And I'm going to stop right there. And I do work various areas, and if anybody wants to do PhD, there is an email address here. Thank you.
They will come to IISc first. No?
If anybody want to do in IISc,
Okay.
go to Sumit.
Thank you. Let's thank Pramod for the nice talk. Questions. So one free tip: if you ask question, then you will get your personalized photograph. Like he is taking my photograph right now.
Good morning, sir. Thank you for the talk. I am Ilina Sinha from IIT Guwahati. I work under John, sir. Sir, you said shapely values. They show the relative contribution of each feature. If we are using zero-shot learning, and maybe I'm training my data on handwriting, like you say, and then I'm trying to classify an apple, and then I'm using shapely values to see the contribution of each feature of an apple. How much can we rely on shapely values to do that correctly? Because it has never been used, the particular instance of apple oranges were never used in the training phase. So can we rely on that?
Right. So first, the easiest answer is I will be in Guwahati for 2 weeks. So I will give answer in detail. But in general, for zero-shot learning, right, this thing is not useful, because you are not going to refine based on anything. You basically have a model, and then you are applying in another domain. Now, if you, technically speaking, even in zero-shot learning, if you saw, we still have a notion of supervised learning, not necessarily using the same design, same model with another design and model. So the similarity to learning you have done, maybe there was something wrong in the similarity learning, you go back. But if you have to iterate on the new model, then it's not zero-shot learning in the first place, by definition.
Okay. Any more questions? Okay, if there is no question, we can thank him once more. From the department, you must small memento. Thank you. Jose is an associate professor in the Department of Computer Science and Engineering, Indian Institute of Technology, Guwahati, where he joined as an assistant professor in 2015. He completed his PhD degree from Indian Institute of Technology, Madras, in the field of computer architecture. He is the recipient of the prestigious Qualcomm Faculty Award 2021 and COMSIS Young Achiever Award 2024 for his teaching, research, and outreach education contributions in the field of computer systems. He served as the Vice Chair of IEEE India Council for a period of 3 years. He is also the core committee member for IISc Society of India Northeast India chapter. His research group in multi-core architecture and systems lab at IIT Guwahati explores the domain of on-chip communication and memory management techniques for large multi-core systems, IoT, embedded system security, hardware accelerators for AI/ML applications, disaggregated storage systems, and communication support for future quantum cores. Over to you, John.
So thank you, Sumit, for the introduction, and good morning to all. Um, so the Oscar-winning session is over, and Sumit don't like tall, dark, and handsome speakers. That's why he put me in that slot of immediately after Professor Prabhat Mishra. He has always left a shoe which is always bigger for all the subsequent speakers to fill it in. Then I was asking Sumit, is there any tea break between our talk so that the people will forget the previous talk? Okay. So thank you, Sumit, once again for the warm hospitality and inviting our group from IIT Guwahati, the Mars Lab students being here. It's a good forum where computer architecture faculty from various institutes in India is meeting. So from the program, I see that there are multiple sessions on memory. So I would be also talking more on memory, specifically on cache and the topic of prefetching. So without much delay, the topic that I'm going to talk is on dynamic technique to eliminate cache pollution in network on chip based multiprocessor system on chips. I will be focusing this work which was published in Cases 2023 and it won the Best Paper Award. And this work was part of the PhD thesis of my student Dr. Deepika Deb, who is currently working in Intel. So this is going to be the brief outline. I hope majority are you from the architecture community, so it won't be much difficult to appreciate what is tiled chip multi-core processors and specifically on prefetching. Then I'll talk about the work which focuses on zero pollution prefetcher and its working principle, and then talk about a bit of the experimental analysis and then conclusion we'll have. As we all know, we are in an era of multi-core processors. From the smallest of mobile phones to large data centers, we have been building it over powerful multi-core processors. The days are gone in unicore, and we are talking about it a lot. So a special category of multi-core processors are basically tiled chip multi-core processors, where we have your processors organized row-wise and column-wise in the format of tiles, and then this is a generic 64 core tiled chip multi-core processor organized under 8 by 8 two-dimensional mesh topology. And there are different kind of internal organization to the tiles, but one such generic one is where each tile consists of an out-of-order superscalar processor, a private L1 cache, and maybe a shared distributed L2 cache that you have. So the entire cache memory is distributed through the full one, and so the L2 cache is basically spread and distributed. So you have one such small chunk of, so 1 by 64th of the total L2 cache is kept in one of this core. That's why it's a L2 cache bank. And then these tiles are being interconnected by an underlying two-dimensional mesh interconnect, the network on chip, which has routers, and then links, which will facilitate the smooth flow of packets between one tile to another. So consider the case that when we have some data need to be brought from this blue tile, from this gray tile, it generates a request and it forces us network on chip packets. So the communication between L1 and L2. So whenever you encounter an L1 cache miss in this particular tile, it has to generate a cache miss request, which in turn will travel through the underlying interconnect, will reach the next tile, the L2 cache portion of that tile, from which imagine if it is going to be a hit in the L2, then the reply packet is being generated and this packet is going to travel through XY routing back to the source tile. This is the typical way by which it is going. And we all know that cache miss penalty is an important component, and always architects are trying to reduce the cache miss penalty component, and we know that depending upon where the mapping happens, sometimes you may have to travel more through the underlying interconnect, sometimes there can be blockages in between due to the congestion that has been happening. So miss penalty is being indeed governed by the efficiency of the NOC routers, the congestion that has been induced there, the buffering, service time, queuing, everything put together. Sometimes it can be an L2 cache miss as well, wherein you go to the memory controllers and go off chip and then bring it. So L2 to memory controllers also we require NOC. So NOC is an important component which has a significant say when it comes to application speed up or the miss penalty, whatever that is going to be. This term may be very familiar to people, but just to keep it at an introductory level, what is prefetching? Prefetching is a technique that will fetch cache block ahead of time. So can you predict it and bring it early? So consider the case that we have a small cache memory with let's say two sets, set 0 and 1, and this is your main memory. Currently P and D are the data that is already located in the cache, and then to have it, I have a miss for a block B which was supposed to be mapped into set number 0. I go and bring B. That's a normal way that you do. That's called bringing a demand block. But if you anticipate that potentially the next block, that's also C, may be required in the near future, so with a single triggering of B, can I bring C also? That is called prefetching. And where do you place C? Maybe I can place it, overwrite that in the cache. So this is one simple way of doing, or else you can add a small buffer here, add B to come here, and C can be kept in the prefetch buffer that it is. So in this case, I am going to put it in the cache itself by going to replace D. So P is going to be replaced with B, the demand block, and C is going to overwrite your D. So this is the way how typically the concept works. And if you look into any cache block that is being brought, the cache block will have different parameters. First is when I am bringing some block from the main memory or L2 cache, whatever it is, you need to know whether that block is a demand block or a prefetch block. And then there is a typical valid bit that is going to be there, whether it's dirty, the tag value, the state associated with that as per the coherence protocol, the LRU bits, and then comes the final data. So we need a lot of control bits in order to manipulate this data. So cache contains, so when you have a system wherein prefetching is enabled, your cache contains demand block as well as prefetch block. And to reduce cache miss, we have to reduce the tile-to-tile communication, which indeed will reduce network call time. But there is something that can happen because your C, that you anticipated that this C can be helpful in the future. In that time, C is going to overwrite something which was already there. What if rather than C, I wanted the data that was already there, then we call it as pollution. So this is an aspect that is going. So cache pollution means the prefetch block evict an important or a frequently used cache block. So when you take any kind of a prefetcher, one of the objective is, can I reduce pollution as much as possible? My subsequent speakers today also will touch upon the aspect of this memory prefetching. So parameter measures prefetch efficiencies. One is prefetch accuracy, is it okay? Timeliness, whatever that I am going to bring, when I am going to use it, and the coverage, how many of my potential future misses that I can hide by prefetching into it. So for consistency across caches, shared cache uses cache coherence protocol, where MESI is one of the coherence protocol that's standard that's been used. So what are the parameters? This indicate whether it's a prefetch block or a demand block, valid bits, then dirty bit, tag, state, all other values. So if you are going for an MESI protocol, the value of the states can be, as you all know, it can be modified state or an exclusive state, shared and invalid, one of these four. When a block is in this E or M state, that means it has the right permission when it is in an M state. The state indicates that L1 cache exclusively owns the block. So think of a case that you have a block that has been moving from your LLC into your L1, and if that is kept in the M state, then there is no point in the data that is kept in the last level cache, because the latest value is available in your L1 cache. Okay, all of the reading and writing happens there, and the value that is there in your last level cache is different from the value that is there in the first level cache because of the W state or M state. So modified blocks stay in last level cache. An updated cache block is stored in some private cache level, but we already know. So modified block consume unnecessary cache space because the latest copy is being available there. So think of a case when I am very busy with the paper submission of my students, I am 3 or 4 days staying late night in the lab and all. So my wife can think he is not going to come back to the home. So my bedroom, my office space can be used for some other purpose.
Airbnb.
Yeah, exactly. So it can be used for Airbnb purpose to hiding out. So if you consider my office as an L1 cache where I am in a modified state, my last level cache, which is my home, that space can be utilized. This is exactly what we are going to talk about. So the modified block consumes unnecessary cache space and power consumption. So look at the case of an L1 cache. If you look at your L1 cache, it can be prefetch blocks sometimes, where the blue blocks what I am going to show. Sometimes it can be demand blocks. So just imagine if you take a snapshot of your L1 cache, it can be consisting of normal demand blocks whenever I am going and bringing it, or it can be prefetch blocks. Now if you look into the last level cache or L2 cache, if you look at the state of those blocks, it can be in 4 different states. Let us imagine if it is going to be an E state and an M state, which has been marked by green colors, versus the yellow color which is in the shared state. Whenever you are in an M state, the block is there, then only it is going to become an M state. Then this I can make use of, because the latest value is available here. Okay, so this is the abstract view. So in order to study this, how many such blocks exist in your last level cache, which are stale blocks, can I make use of them? We conducted some experimental studies since I was working on 64 core processor with out of order processing, and these are the standard cycles that we use, the parameters. We worked with the parsec and the spec workloads and Gem5 tool that was being used for power and all.
In a write-through cache, you won't have this issue, right?
No, no.
Always be writing through. So you're assuming a write-back.
We are going to assume it's a write-back cache between L1 and L2. So typically, because if you are going to keep it as the write-through, there is a lot of traffic between L1 and L2. So here it has been assumed it is write-back. Okay, do existing prefetches causes cache pollution? That's what we are taught. So all what you see in the x-axis are standard state-of-art prefetchers that we have. They all have some level of cache pollution because it is going to overwrite the space in L1. And depending upon that, you can see that it varies from 20% to 55% that has been there. Now, what is the percentage of stale blocks? Do you really have stale blocks? The meaning of stale block is the block is kept in an M state. How frequent is prefetch request generated? These are the studies that we did. So let us try to understand this graph for one of the parsec benchmark we were trying to see. The green one indicates how many modified blocks are there across the time window. We have been showing across the million clock cycles. So the green one shows at some point of time there are more stale blocks, some point of time there are less stale blocks. That's what you see in the green one. And how many prefetch requests really came? That is the red one. That also depends upon the number of demand misses and all. So what is the conclusion here? We have a lot of unused spaces or a lot of stale spaces that has been shown by the green color. Can I make use of these unused spaces for this red request? As long as it is lower than that, I have some space that isn't available. So I am not going to overwrite anything on my L1 cache. Whenever I wanted to prefetch, I bring them and put it in the L2 portion of the same one because it's an unused space. Since I am not going to overwrite anything, pollution is 0. But I have to go out of L1 and go and bring it.
Then couple of quick
Yes, sir.
So are you assuming that you're going to do prefetch for L1?
Prefetch for L1 and keep it in the same time.
Okay. And second thing is you are not assuming any prefetch for L2, and the prefetches that you do in your original design directly come to L1 without touching L2.
Yes.
Correct? All these things are assumed.
We are not going to work on what is a prefetch. We are only going to work on the placement of the prefetch block.
I understand that, but I'm saying that any block which is prefetched for L1
Yes.
by default is not put into L2.
Yeah.
Correct? That's your
The block that I am bringing for L1, that is.
Otherwise, if you assume that it comes to L1, if it's an inclusive cache and if it comes to L2 and then L1,
Yes.
then this doesn't tracker at all because it's anyway there in L2.
Yes. So what I am doing is that the demand block will directly come to L1. The prefetch block I am not going to keep it in L1 at all.
That's in your zero pollution scheme.
Yes.
But your baseline is that any block which comes to L1 comes directly to L1 without touching L2.
Yes.
So it's a non-inclusive.
Yes, because this L2 is not yours.
Huh?
This L2 is not yours. Your L2 is scattered across. It's a shared distributed L2. This is just only placed in that portion of the tile. Rather than one chunk of L2, it's a scattered distributed L2.
And the graph what you showed is the amount of space available in a particular tile or in the entire tile?
In the entire one. Yes.
So, where is the memory node connected?
Memory?
Memory node connected.
Memory node for this assumption is connected in the corner tiles.
Corner tracks. Then
Corner.
I think I can probably tell you about this thing. So, typically what we do is to optimize the traffic. We don't go to the shared cache and we go directly to the private cache to optimize the traffic between the memory node and the requesting code to reduce the latency.
So that's happening when it's an L2 miss, that's what's our told, right? When it's an L2 miss, when you bring from memory controller, we can directly forward to L1 and the copy can go to L2.
Yes.
That's an
Yes.
optimization. That's
Yes.
what we want to do.
Yes.
Okay. My question is more like whether it's an inclusive cache or not. Actually, it's not an inclusive cache.
So what is zero pollution prefetcher? Your intelligent caching of prefetch block. So I am not going to work anything on what to be prefetched. Whatever algorithm you can use for prefetching, where are you going to place it? So intelligent caching of prefetch block in stale locations of L1s. What type of prefetcher does GPP uses? Your L1 data prefetcher trained with L1 cache miss. Where does GPP place prefetch block? In modified locations of last level cache of the source tile which is being generated. Okay. This is an inclusive cache, sir. Because you are bringing from L2 to L1. You are keeping it as close as, you are keeping it in the tile of L1 and just making use of that space for keeping. It's an inclusive cache.
Okay.
Do you have any doubt in that?
Yeah, if the home location, if the L2 home location for a block is a remote tile,
Yeah.
right? And
From there you bring it to the source tile.
so you'll have two copies of the block.
So suppose what happens if it is a prefetching? You are going to keep it. Rather than keeping it overwriting a set in L1 cache, I am keeping it in a buffer.
Right.
Rather than the buffer, it is now
Anyway,
stable.
L2, your local L2 is something like a victim cache of L2.
Yes, correct.
So I guess it's inclusive globally, if everybody is globally.
Globally, it's inclusive between
But not
L2 and
locally.
L1.
It's not inclusive locally.
So rather than using a prefetch buffer, I make use of the stale location in the local tile that is available. Okay. So what are the benefits of CPP? It eliminates cache pollution. So and then it reduces L1 cache misses as well. It utilizes LLC efficiently as modified location contains stale data. It reduces network packets generated because there is no cache pollution that is coming and bringing up and down. So what is the working principle? Prefetch block upon reaching the requesting tile, it searches for stale modified location. So we require some additional hardware in order to do that. You place the prefetch block in the stale location. So you have the L1 cache and the piece of the L2 cache, and we are adding a new component which is called tracker. And then tracker will have the tag details and the data is going to be kept here and the tracker has the corresponding tag. So when you bring some prefetch block, when you bring the prefetch block, the tag is being kept in the tracker side and the data that is going to be kept in the LLC portion. And then when there is an L1 cache miss, you look into the tracker if the tag is matching, and along with the tag, with the data structure of the tag will tell you where it is exactly that is being kept, and then that will help you. So rather than going all the way to the distant L2 without generating an NOC, because these two are connected in the same time, so there is no NOC packet that is being generated. Okay, so prefetch block mapping and what is the structure of the tracker, and then how do you place it? And the biggest portion is once I am done with my work in the office, I come back. If I see it's already been outsourced to someone else, how do I handle it? So that was the last tricky portion which we struggled a bit in order to get that. So tracker is nothing but the additional hardware that you use in order to keep the tag of it. So tracker tag size is equal to the L1 tag size for easy prefetch block mapping in the tracker. Because there is a variation in the tag size, there is a potential set of possible L2 entries. So tracker use basically 5 fields, a valid field, a tag field, and then the combination of the L2 sets. You cannot freely keep in wherever that you want because the tag bits is same. So the possible set of L2 and the way in which you are going to keep it. So this bit of the bookkeeping data, I am not going more detailed into it. And L2 cache uses two additional flags, one E bit per set, whether it has a modified block or not, and one P bit per block, which block is placed in L2, whether it is its own modified block or it's a prefetch block by nature. And when you bring prefetch block, you have a prefetch block on reaching L1 try, it will search for the sets and then finding out to determine the address and then keeping it. For the L1 set, the L2 mapped set is indexed. There are, like what I told, it's been so restricted to few of them. If E bit equal to 1, the L2 mapped sets, state field of all the ways is being searched. So these are all the bookkeeping details, all what I wanted to know, and additional hardware that is being added. So along, if there is an L1 cache miss, you look into this. Normally what happens, it go all the way through NOC and bring it. Had it been a normal prefetcher, I am going to overwrite this. I am not going to do any one of them, I am trying to do. So this is the additional miss penalty that you get. Okay, and then this is the last and the most challenging portion, prefetch invalidation. So invalidate a prefetch block when original LLC block, the luxury that we had is I am in M state. The moment I am not in an M state, I wanted to come back and all, what will I do with that? The most simpler thing is kick you out, whoever is the unwanted guy, kick him out. But I put in a lot much effort in bringing him, then I have to throw him out. So there are three different variants that we propose, CPP using three different policy. One is no reordering. A prefetch block is simply evicted out of L2 and from the tracker. The second one is, okay, this, now he is coming back, so can I find some other place in the L2? So some kind of reordering is being required, that is CPP with reordering. So prefetch block is remapped to a different stale L2, so accordingly an update and tracker is required. The third one is, I will hope between these two. At some time I will kick up, depending upon the traffic, depending upon the available number of blocks. Sometime I go for this based upon some threshold condition, we worked upon some selection criteria. So basically it's going to work with this. This can take either this shape or this shape. Now looking into the performance of GPP, different, we have the multi-threaded benchmarks and then multi-programmed benchmarks. So what we talk it as a demand hit is a system without any prefetching. That's a green portion if you take. And the red portion is if I am going to have some good prefetcher that is being done, then the percentage of hits is going to increase. And the top portion, the yellow portion that you see, is the additional number of hits that you are going to get with CPP. So if in the case of CPP, if the total number of hits that you are getting, basically 50% of that is normally your demand hits, a good prefetcher will improve and your CPP is going to improve little more. So you can see that across benchmarks and based upon the property how it is going to navigate. So the additional yellow is the benefit that you get. Now if you look into
John?
Yeah.
You used the MRU policy for the tracker, but you're using MRU for the earlier cache things.
Yeah.
What is the reasoning for the MRU we use?
No, we are just using the bit combination. The same concept is this because the tracker is not that big. So if you want just most recently used only just one bit is being required. The other one you have to evict the recently used one. So not too much of a difference. This is only just one bit, 2 bit. Okay. So now if you look into the useless prefetch packets, BOP is one of the state-of-art prefetcher, and here we are not bringing anything useless. The only way how it is being treated as useless, you brought with lot of hope, but later that block was no longer stale, so you have to kick them out. That traffic is basically useless. And then the demand misses, since you know the technique by this now, these are the three variants that we proposed, and this is no, with respect to a baseline, no prefetching technique, and these are all different state-of-art prefetchers. Across all of them you can see substantial reduction. This one is multi-threaded benchmarks and multi-programmed benchmarks. And the accuracy that you can see as expected, since you have more space, your accuracy is going to be improving there, you are not going to throw them out. And the coverage also is significantly better than the other one. Okay, and if you look at the performance, because I told it is going to move across different domains, there are three variants proposed, so we saw that which version is going to work. One is no replacement. So out of the total 100 cycles, some cycles it was working. The green portion so that it was operating under ANOVA mode, other one is operating under the rescheduling mode. Okay, so this is the work that I wanted to brief here. And cache misses were substantially reduced, and then obviously, so network stall time because the number of packets entering into the network is there. And average memory access time also was been significantly reduced, and then this is the overhead in terms of the logic circuit that has been added. So to conclude is ZPP utilizes redundant location in last level cache for prefetch block placements. It completely eliminates cache pollution for TCMP architectures in comparison to contemporary prefetchers. In applications where majority of the blocks are shared, I thought someone will ask this question. The base route is you have a lot of M blocks. If you don't have enough M blocks, then this is not going to work. So those applications where there are a lot of writes that is been happening, then that makes it an ideal candidate to be used. CPP is ineffective as it would require frequent PF invalidation. So you bring it, then quickly it's going to become a non-shared mode. It can be a cost-effective design. That's what we thought.
How about only exclusive blocks?
Yeah. So in that case also the copy is same there and here, but the cache coherence protocols has to be worked more. You have to write one more control logic which will handle the E cases as well. So
Yeah, but those are the candidates also. Right?
those are also the potential candidates. We could get little bit more savings for that, but we tried with
Actually, you make it more savings because I don't
few more blocks we'll get.
So if these are multi-threaded benchmarks, then the sharing pattern might be high. But then for a single-threaded benchmark and even for multi-threaded benchmark, if the sharing pattern is not high, then most of the blocks are exclusive blocks.
Yeah,
Right? So in those cases, you might.
we can use that candidate for that as well. Yes.
So do see significant advantage in multi-threaded workloads then? Because assuming that there is more shared
See, this one, suppose if it is a multi-programmed workload also, this is not your property, it is somebody else's property. So that depends upon what they use. It need not be across all cores, it has to be sharing that is been available. Let's say this is a multi-programmed workload's data and it's going to be returned there the moment this is low. So we found that there is not much difference that is been happening. Whatever be the core that is been doing, his copy in L2 is your potential candidate. The moment you write, that copy becomes state.
Correct. So typically multi-threaded programs will have a fair amount of shared data, right? I mean, you're going to have
Sharing is not going to help you. You want modified category. You should want more write-intensive applications help you.
correct. And so, what is your configuration in terms of number of cores and how many multi?
There 64 cores. So we tried with a different combination of benchmarks. Let's see. So the one that you see here on the left side is the multi-threaded benchmarks, and these are the multi-program benchmarks. Combination of spec benchmarks in the different cores. So we don't see much of a difference in performance. Whichever is a write intensive, we get benefit.
And what if you know more about the prefetcher? I mean, can you optimize this further?
Yeah, see, if you improve the performance of the prefetcher, still you have, like what to bring we are not going to choose. So what to bring is been taken by whatever prefetch algorithm. So it can work with any prefetching algorithm. This is just a placement technique.
True. So what I'm saying is, can you use the fact that if you know more details about the prefetching algorithm, can this be better?
Yes, then the accuracy would be more.
So is it like those prefetch requests are, you're assuming what percentage of them will hit in L2? Those prefetch requests which you are bringing into L1, what percentage will hit in L2? And if it is not hitting in L2, isn't it going to saturate the memory bandwidth? So because most of the prefetching, the main problem is that you just saturate the memory bandwidth and you don't gain a lot out of that.
Yeah.
So any study is...
We have not done any study because we are just looking whether it's hit or miss. Whenever you bring it and place it.
Okay.
So we didn't work on improving the accuracy at that side as well.
Okay.
Yes.
So coherence algorithm have to take care of
Yes.
no, the prefetched blocks which is there in the local L2.
Yeah.
How do you keep track of this?
So the tracker and this unit, so it's from an L2 perspective, it has gone to L1. I have given a copy to L1. It's as good as like keeping in L1.
Okay.
Rather,
And you will invalidate it from there downwards, is it?
yes. you can keep it very simple that you are been keeping it in L1 only rather than keeping it L1. It's an extended L1. Some space in the adjacent L2 component.
But this requires your entire coherence protocol.
Coherence protocol was changed. That was overhead.
And the controller has to be changed.
Yes, that was overhead.
Okay, more questions? No questions? So all the questions are coming from faculties, by the way. That means faculties don't understand, all the students understand everything. Or it may be the other way around. No questions? Okay. Faculties are the confusion.
Yes, sir.
Hello, sir. We seen that the graph. If the m block suddenly reduced, what?
Then there is no choice. See, you are going to bring somebody, but there is no space available.
So we will
discard.
take it out, whatever.
You will discard. So you are not going to bring only if there is a space. You will bring, and if there is no space, then that packet is
We
wasted.
bring some blocks, then the m block reduced. Then we will keep it.
We are not going to place it anywhere. It's discarded. So it's less you are going to a car parking area, hoping that there is a car parking space available. You go all the way there, no space available, you come out of it.
No, I'm asking that we already parked some cars in there. After that, the space reduced.
Yeah,
M blocks reduced.
reduce. Then it has been
We'll
kicked out.
kick out the.
Kick out.
Okay, any more questions?
Still you can meet me during the break or lunch time.
Yeah, sure. If there is no more question, we can thank John once more. In the department, there is a small memento. Thank you. Thank you. Thank you for coming. Okay, we will not forget John's talk. We will discuss more over the tea break. open that hand rail, there is a desk inside. Okay. Okay, and thanks Devi Prasanna for pointing out. He is saying not a desk, it's a fancy desk. Yeah, so you can keep your laptop or copy there and you can write.
Discovery.
And another announcement is all the talks are being streamed live in YouTube. So if any of your friend or any of your student wants to listen to the talk, they can just go to the CSA's not website, in the YouTube channel. The link is also there in the website, the workshop website. They can go there and listen to the talk online, the live stream. Okay. Hopefully you had a good tea break. Let's welcome the next speaker, Sparsh. Hold on. So John has so long of a bio that I have to scroll and then get the other bios. Sorry, I could have.
Yeah, I think one line is enough.
Yeah,
That's
I
all.
also need to find that one line. Dr. Sparsh Mittal is currently working as an associate professor in the ECE department at IIT Roorkee, India. He received the BTech degree from IIT Roorkee and the PhD degree from Iowa State University, USA. He has published more than 120 papers at top venues and has nearly 9,000 citations. He has received Best Paper Awards or honorable mentions at AIML Systems, VLSID and ICPR. His research interests are AI for computer vision, applications of AI, computer architecture and VLSI. Over to you, Sparsh.
Thank you. Thank you so much for the introduction. So I feel, systems researcher is a very, very, rare species. And if at all, if you were all not working on this, we would become extinct by now. So very, very great thank to all of you. And special thanks to Sumit for organizing this. So actually probably we are the real minority, right? So we have to kind of present. So, okay, so coming to my research presentation. So today I will present our work, which we published in Cases. The title of the work is VADF, a versatile approximate data format for energy efficient computing. And at the end of my presentation, I will also share some, retrospection or introspection on my research journey. So I hope it will be useful to some of you. So let me first introduce what is approximate computing. So we all know that for many of the emerging applications like AI, ML, and so on, we need immense amount of computation and storage. And conventional computing architectures are not capable of fulfilling that demand. So we need to do some compromise. So approximate computing, usually that compromise is between performance and energy efficiency, right? But approximate computing, usually we kind of keep the accuracy fixed. We just have a trade-off between performance and energy. But in approximate computing domain, we realize that many applications are error tolerant. For example, to our eye, whenever there is a video and the frame rate is beyond 30, so if for a video, if the frame rate is beyond 30, whether it is 31 or 46, it doesn't matter because our eyes cannot distinguish between that, right? Similarly, you can compress an image and most probably the eye will not even recognize it, and so on. So there are many multimedia applications, image processing applications, and many other applications where we have a huge amount of data. Not all of that is really useful for coming to the final result. For example, for pi, right? We always work with pi equals to 3.14, whereas the actual value of pi is maybe trillions of digits after decimal. So, but for most of our tasks, 3.14 is more than enough. Right, so that is where we have been working with approximate computing, probably we did not recognize. So in approximate computing, we relax the accuracy and we gain a lot of energy and performance. So a slight violation of service level agreements can still be acceptable to the customer, and you can gain a huge or sometimes disproportionate benefits in terms of performance and energy. So there are many applications. I will not go into detail, but now let us come to the next step. So now approximate computing can be done at the various levels, at the level of algorithms, at the level of architectures, at the level of computing. For example, you can have an approximate adder, approximate multiplier. So, but in this presentation, I will talk about approximate storage. So if we can store our data approximately, we can we will of course lose some amount of precision. For example, if I store 100 as 99 or vice versa, there is some error, but for most application it may be easily tolerable. So we save storage energy, and we can also compute on the narrow narrow data. Instead of working with a 32-bit data, if I can work just with 8-bit data, my compute energy will automatically be stored. So this approximate storage is very closely connected to approximate computing and vice versa. So they also give us area, delay, power advantages. Usually the usually 8-bit adder will be much faster than a 32-bit adder. It will have much less area, it will have much less power. So of course it's not a universal solution. So for example, for cryptography kind of application, even 1-bit change can have a huge impact because of this avalanche effect. So approximate computing is not meant for every problem in the world, but it's still good for many problems. So now in approximate data storage, we compress an n-bit data to k bits, and then we can perform operation on k bits, or we can recover back n bits from those k bits. There will be some error during the recovery process, but as I said, it is acceptable to us. Now, so this much work has been done. Now the next question we ask is, what if there is a soft error in the data that is stored approximately? Now approximation itself has introduced some error. On top of it, if there are soft errors, then how do those approximation induced errors and the soft errors, how do they interact with each other? In the worst case, they can compound, right? Or they can exacerbate the error introduced due to approximation. So we need to study all those issues, because soft errors is a real problem in many real world scenarios in many data centers. So in conventional computing, we use error correcting codes for correcting the errors. But now here, how do we use them? That is another question we have to explore. So we work with an assumption that there is no error correcting codes that are used. So we want to ensure and of course, if error correcting codes are still used, they will further give stronger reliability. And we work with a 1-bit soft error model, which is a fairly well accepted assumption. So let us start with the very naive or basic technique. So in a basic truncation technique, if we have a 32-bit data, we can truncate it to a smaller number of bits, right? So and slightly more intelligent technique is that we extract the most significant bits from the original data. For example, if the number is suppose 2 to the power something plus 1, we can just ignore that plus 1, so the number just remains 2 to the power something. And then if the number is stored as a 2 to the power something, then a lot of the LSBs will be 0. So you can then truncate it. So it is like a very natural approximation. Now these are the previously proposed works which do slightly more intelligent approximation. I'll just explain, for example, this one. So here many times it happens that our value is much narrow than the storage that we have provisioned for it. For example, in C++ or C, when you do int x equals to 4. Now int means 4 byte, that means 32-bit variable, whereas the number 4 only needs 3 or 4 bits. So in a 32-bit variable, you are only storing a number of just 3 or 4 bits. So most of the MSBs will be 0, right? So if most of the MSBs are 0, so for example, many of the for loops, we say I equals to 0 to n. Most of the time I will remain 0. So not 0, but small value. I will go from 0 to n. So if n is also small, then I will always remain a small value. So that's why most of the MSBs are usually 0. So in this FT-approx technique, they first of all divide, suppose this is the 32-bit number, they divide into blocks of size 4 bits. Then they start from the MSB, they find out which block has the first or the leading, what we call leading one. Suppose this block number 5, so my counting starts from here, 0, 1, 2, 3, 4, 5. This is the most significant valid block. You can say, I mean, they are not actually invalid, but this V means just something which has value. So we save this block and this block, right? So I have saved just these 2 blocks, and I have to remember that what is this number 5, because otherwise we will get confused whether this block with most significant one appeared here or here or here. So I have to store this number 5. So that number 5 is actually somehow stored here, 101, and this is just a control signal. Like whenever we do error correction, there is always some redundancy we add. So to this number 5, we also add some redundancy, just like there is a dual modular redundancy or triple modular redundancy. So there is a redundancy we add. So this control signal just tells us that this most significant block starts from number 5, and we have now if some soft error occurs, if I were to just store the number 5 and a soft error occurs, that 5 can become 6, right? If suppose this number, I store 5 here and a soft error converts this 5 into 6, then I will assume that this is not coming from here, but it is coming from here. That is like multiplying the number by 16 times, because 4 bits means 1248, right? So that means I have to really preserve this location where this most significant one occurs. This data itself, if some soft error occurs here, that will have less impact. Suppose if soft error occurs here, it will only increase the number by 8 times. But if soft error occurs in actually 5 versus 6, that will increase the magnitude by 16 times. That's why the location where this most significant valid block occurs, that is much more important than this data itself. Right? Once I have stored in a compressed format. So I have to really preserve this value, this location number 5. So that's why I have this duplicated, so that there is no, I can protect it. And similarly, AIF also partitions it into fixed size blocks and so on. So now the limitations of these techniques is that when some error when some soft error happens, they can induce much more error than what our technique can tolerate. That means they do provide some level of protection, but not sufficient protection from the soft error. And and one more key idea that we introduce is actually a bit camouflaging mechanism. So if you know how IEEE 754 format stores a floating point number, there is a leading one. If the number is normalized, there is a leading one, and that leading one is not explicitly stored. So we also use that idea. So if that leading one is not explicitly stored, then that one is always protected. If that leading one is never, so because we always make this assumption that leading one is always 1, and we don't explicitly store it, so that one is always protected from the soft error. So just by this technique itself, we have reduced the effect of soft error by half. So that I will show the results later on. And one more thing is actually our technique also offers flexibility to compress a number. So suppose if the number is originally 32-bit, our technique offers this flexibility to store it in 16 bits or 24 bits or 12 bits or 8 bits, depending on your budget. Whereas previous techniques like this technique doesn't offer a very clear-cut mechanism to store it in like 12 bits or 14 bits or 20 bits. That flexibility is not offered by previous techniques. So let me explain our technique. So how do we work? We first of all we have a scheme that we will store the parity bit, error correcting bit, the location bit, and the data bit itself. So these are the 4 components of our storage format. So for this we find out the significant bits in the data. So just as in this technique, they find out which block has the most the leading one. Instead of finding the block which has the leading one, I find out the exact location of this. Right, starting from here they are finding this is the block number 5. But if you really see, this is like 4, 8, 12, 16, and 20, 21, 22. If I were to store the exact location, then it is not block 5, it is the location 22. So instead of storing the number 5, I have tried to store number 22. Now that will take more bits, because here there are only 8 blocks, so it only requires 3 bits, whereas I will have to store the exact location that will require 5 bits. So that's a trade-off I am playing, but that gives us more flexibility, as I will show later on. So we find out the most significant 1 bit, and then we protect the data from soft errors by also storing the error correcting code and the location. So this is, as I said, this is our overall format. So this is the our original number is n bits. I store into c bits, where p is the parity bit. We all know parity is a very simple, straightforward mechanism. There is an odd or even parity. Then this is my data bits, and these data bits are only for the starting from the most significant one, excluding that one itself. And where did I find that most significant one? That location is this M. Okay, where did I find that most significant bit? And this E is the error correcting code for this M, not for this K. It's much more, as I explained in the previous example, it's much more important to protect the location where that most significant bit occurs rather than the data.
Question.
Yeah, please.
I don't understand why error correcting bits are required. Like what errors
Yeah, I'll show just
you
one.
anticipate?
Yeah, just one. I'll show. I'll take an illustrative example. Like just 1 second. Come back to the slides. Yeah, here. So I will go back to the actual explanation. But let us take this example. Suppose our original number is this 16-bit number, right? This original number is a 16-bit number. Now, forget this last 3 columns. I don't use any approximation technique. It's just a conventional system. So actually there is a soft error, as we told, like alpha particle can strike from, either from cosmic rays, and there are particle strikes from I think other industrial sources also. So they can flip a bit from 0 to 1 or 1 to 0. Because SRAM stores is charged. SRAM stores the data in the form of charge. So a charged particle can transfer its charge to that SRAM, and it can withdraw the charge. So it can 0 to 1 or 1 to 0 flip can happen. That is the meaning of soft error.
But isn't that an orthogonal concern to your work? So even if you don't have the data compression, such bit flips can happen.
No. Our basic problem is that we want to study their interaction. I mean, compression. See, approximate storage has been studied before, but nobody has. Except this AIF and this FTApprox work, nobody has studied their interaction. We explicitly state our research problem that what if error happens in a approximate storage, then what will you do?
Is
So
the
not
impact more in the approximate storage, is the impact of the error more?
Yeah, so actually I'll come to the results. Maybe I'll show. For example, these are the sample examples I've shown you. So it can be possible. For example, here the original number was 5306, and here we did not use any kind of compression. And assuming the worst case that MSB gets flipped, this 5306 becomes 38,000, which is a huge error. Now FTA, it uses some kind of approximation. I will show the detail later on. So here, once this MSB gets flipped, the number becomes 37,000 something. So which is close to the unprotected or uncompressed number. Whereas in our technique, because this one was anyway hidden, so this is just for showing. I'm showing you, but it's not explicitly stored. So what is explicitly stored is just this number. So even if this bit gets flipped, the impact on the magnitude of the number is much smaller. So that's how we have protected this. So it's like a proactive strategy to protect the number while also reaping the benefits of compression.
But you give up some bits for the error protection code.
Yes. So there is some, as you see here. Here. Suppose even if there is no error which happens, some error, even if no soft error happens because of this compression, it's like a lossy compression. There's a huge research study on lossy and lossless compression. If you, from that perspective, our approximate compression is a lossy compression. So there is some error will happen. For example, instead of 5306, the number has become 5248, even if no external soft error happens. Similarly here in that example, 5306 becomes 52. Okay, the same number, but this 75 becomes 72, even if no external soft error happens. So that means there is an error of 3.
I'm sorry if I'm wasting time, but I didn't understand why the difference.
Yeah, because we have ignored some of the LSBs.
Okay.
We have ignored some of the LSBs. So let me explain, then this will become more clear. Yeah, here. So just a minute, I probably missed some slide. Yeah, so let us start with this slide. So this was our original. Suppose let us take this example, illustrative example. We have a 16-bit number, okay, and the leading one appears at the location 11, starting from 0. The number 0 starts from the right. So now I want to compress this 16-bit number into smaller number. Suppose n equals to 16, and I take this k is actually how many bits after the most significant bits I actually store. So actually after 11 there are 11 more bits that I should have stored if it was exact storage. But because it is approximate storage, I only choose 5 bits and rest of them I have ignored. So you can see this last 6 bits I have ignored, and that is why the error is coming. Okay, so instead of storing all the 11 bits after the most significant 1 bit, I have only chosen to store 5 bits. That's my configurable parameter k equals to 5. So here, these are the data bits I will store. So if I already fixed k, so if k equals to 5, I will only store 5 bits. But a corner case can happen. Just to suppose my most significant bit is this 4, and then there are no 5 bits that are available after this most significant 1 bit. So then, we can always add a 0 in front of any number, like 5 and 0, 5, they are same. So just for storage purpose, I will append a 0 at the MSB side because it doesn't change the magnitude of the number. Okay, so that is just explanation of how do we store only some bits, only k bits. Actually my number is n bit, I have n bit data, but from that n bit data I am only storing k bit data. Okay, and as I said, there are 4 components of it. One, which is the parity bit. I will not explain about parity, it's very obvious. Then these are the data bits, and where does this 11, right here, the most significant data bit appears at 11. So, and that will require me 4 bits because 16 log 2 is 4. So log, and this is the location, and then E is the error correcting bit on that number 11. On that number 11, I have to use error correcting bit. So that is this. So let us take some more example. Now let us here is one more example. My total data is n equals to 32. I want to store that 32 bit number into 8 bits. Okay, so here this is the 32 bit number stored in 8 bits, and a VADF format can be specified just by these 3 numbers. So this E is the last number is the number of error correcting bits I am using. Okay, so here I am using 0 error correcting bits because once you are compressing it so much, there is no scope for error correction. And then I will explain this. So here, let us start. So here, the most significant, that means the leading one appears at the location 25. So I will store, this is the number 25. I will explicitly store this number 25, and this is 1 bit parity, no need to explain. And then after this most significant 1 bit, I will take here only the 2 bits because this total has to be 8 bits. I am compressing this 32 bit number into 8 bits. So after this 1 bit of parity and k equals to 5, so 5 bits of data, I am only left with 2 bits. So only 0 and 1 I store here. That is case 1. Now I don't want to compress it so much, I will just compress it to 12 bits. And so out of those 12 bits, my data bits are, I have to use 4, k equals to 4. Okay, so again the most significant 1 bit or the leading 1 bit appears at the number 25, and these are the 2 error correction bits. I will explain this bits how I got the value of this 0, 1 in the next slide. And starting from excluding the 25 itself, I will store the next 4 bits. Now you will see that instead of storing 0, I am storing 1. Why? Because when I am doing truncation, right? When I do truncation here, I am truncating all these bits. So instead of directly storing only 0, I do OR operation between these 2. That is actually called rounding. 0, I do an OR operation between this 0 and this 1. So the OR operation result of this 0 and 1 is 1. So I store this 1. Okay, this is a small way to kind of error compensate for the error. Similarly, I can store it in 16 bits. So here there are 4 error correction bits. So the 16,4. So this is the 4, and I store k equals to 6 here. So this I store 6 bits after that leading 1 bit. So that is actually 0, 1, 0, 0, 1, 1, 0, 1, 0, 0, 1, 1. That is how I get this 16-bit number. Okay, and similarly this FT approx I have already explained. Now this error correcting code, actually I will skip. This is simple, Hamming code scheme. We have all studied in digital logic or digital electronics course. So we can decide suitable number of bits, and if we have more number of error correcting bits, we can simply duplicate a one of those bits. Right? It's very simple. Now, to compare it with these are very naive schemes. They are not proposed by somebody, but they are simply naive schemes. So here we can do a fixed size truncation. We can, to compress n-bit number, we can simply store the top q bits. For example, here, if it is an 8-bit number, I only store the top 3 bits. So here it will lead to huge error for this particular case. But this is very naive or unintelligent scheme. And MSV aware truncation is that I find out the most significant bit and I store the location also, and I keep where was that location found out. So now let us take this example. So let's take a simple 8-bit example. This was my original data. So here in this, if the MSV gets flipped due to soft error, then this 75 will become 203, which is a huge error. Now in this EIF scheme, we actually truncate some of the bits, and remember that okay, I had truncated the last 2 bits, so I just ignored this 1 1. So here you can see because I ignored 1 1 is just the number 3. So instead of 75, the number becomes 72. It's like chopping off the last 2 bits. So error is of only 3. But here the point is, if after I store this data and a soft error occurs in this most significant bit, the number will become 200. So the number which I stored as 75, it has become 200, which is no worse than if I had not compressed it. That means I used approximate compression, did not benefit a lot. Whereas in our scheme, we will use this, here starting with this 1, I will, I will just store k equals to 3 bits. I will only store the next 3 bits. So 1 is actually there. It is not explicitly stored, but actually it is there. And this 001. And we have truncated 3 bits. So we will multiply it by 2 raised to power 3. So here this number is also 72 if there is no error. But if there is no soft error. But if soft error occurs, because I am not explicitly storing it, I am only explicitly storing these 3 bits, the error will happen in this bit. So this number will only become 104. So 75 only becomes 104, which is much better than this becoming 200. And similarly, this case, here k equals to 6, that means after this number I am storing these 3 and these 6 bits. So error can only happen in this 0 becoming 1, which will still be much less harmful than it happening in the original number. So there are, so this is the basic idea or the key idea. Now let me quickly explain in what ways we can use approximate storage, what are the usage scenarios. So usually in the conventional approach, we use the data and we use the ECC separately. So that will require me a separate storage. Now here I can compress my data from 32-bit to 4 bits. So 32-bit to 12 bits, and I can have just like the conventional SecDAD, ECC, and so on. So I can save. That means the storage I save, I can utilize that for storing ECC, right? So that means I can fit everything within a storage count which is power of 2. So that way, either we can, like whenever we do compression, we can use the compression for either improving the speed or for improving the storage efficiency. Similarly here, what we are claiming is that this ECC we can store in this number. So this ECC is separate from the error correcting code I am using in my own protocol, in my own scheme. And one more opportunity which I explained at the beginning is that once I use approximate storage, I can work on those narrow data. So that I have to use narrow computing units. For example, in the conventional approach, if my numbers are 32-bit, I have to use a 32-bit adder. But once I compress the number from 32-bit to 8-bit or 16-bit, now I can only work with 8-bit or 16-bit adders, which are much more energy efficient, area efficient, delay efficient. And once I get the result, I can do inverse. Now, of course, some error will happen, but our basic premise is that some errors are acceptable.
But this is compounding error, right?
Yeah. No, actually, compounding in the sense, there is error in input 1 and there is error in input 2, so that will get compounded. Yeah. Yes. So I will measure actually what is the impact. So of course from 32 to 8 it will be huge error, but 32 to 16 it will not be as large an error. Now in approximate computing domain, there are certain metrics. These are standard metrics. One is called mean relative error distance. So this is the actual exact accurate number, and this is the approximate number. So we find out the magnitude, absolute magnitude difference between them, and find out the like a percentage or the relative value, and average it over all the numbers. Similarly, max RED shows where is the maximum error, because in many applications, not just average error, but the worst case error is also very important. And MED is simply the absolute difference without doing any relative computation. That means it's just the magnitude of the error itself, not the relative error. So here, this is the MED results. This is the MED is maximum absolute distance simply means errors, right? Distance means from the original number how distant, how far you got. So these are different protocols. That means from 16-bit number I compress it to 7 bits and so on. So with this fixed size truncation, there is a huge, like for example, there's a huge mean error distance is huge value, and whereas with our technique, because we have done it very intelligently, it is much less error. So here what we do, we actually generate suppose 10⁶ random numbers, right? It can be completely random, or it can follow some distribution like uniform or Gaussian or Poisson distribution. So that is how we generate these input numbers, right? And then pass them through VADF and see how much errors are happening. So here are more analysis. So starting with n equals to 8 or 16 or 32, we use m is the number of location bits, because if you have 8 bits, then it can compress to 3 bits and so on. And the CF is the compression factor. That means if 8 bits get compressed to total of 6 bits, then the compression factor is 1.3. If 8 bits compress to 8, then it is just compression factor of 1, and so on. So if 32 bits get compressed to 24, then the compression factor is 1.3. So we have compressed for various scenarios. We have compared it with FTapprox and EIF. So for the comparable compression, here, so for example 32 bits getting compressed to 8 bits, our MRED is 6.61. Whereas this in this FTapprox, actually FTapprox cannot compress it to 8 bits. Let us compare it with 32 bit getting compressed to 16 bits. So we have a compression factor of 2. Our MRED is 0.4, where their MRED is 0.58. That means MRED should be as low as possible. They incur much higher MRED. And here also actually this EIF has much worse result. So no need to talk about EIF. And these are the other use case actually I mentioned. We can after compression, we also do we pass them through approximate computing units, so that our computation energy is also saved. So this is the 1A scenario, which is the baseline scenario where we use accurate adder. Now instead of 32-bit accurate adder, I can directly use a 32-bit approximate adder. Right? That means there is no approximate storage, it is only approximate computing, and I can do approximate storage and exact adder, but it is 8-bit adder. And we can go further, which of course may not be very realistic, but just to showcase the results. Once we do 8-bit input, compress from 32-bit to 8-bit, I can do approximate adder in the 8-bit itself, and then compute the results. So with that baseline, this is the baseline. I can compare this with this, this with this, this with this, right? How much is the relative savings? So these are the results. So 32-bit adder has this much area, power, delay, and energy. Now once we compress it to, I think 16 bits or anyway, I think it's 32 bits compressed. I think should be probably this one of this is 8-bit or 16-bit, probably some error here. So once we compress it either to 16 or 8-bit, actually I have to check. Then there is huge saving in the area, power, and delay, and energy is also saved. Similarly, when we check it for the entire end to end, that means not only computation, but because we have to do also the inverse, because VADF number formula itself cannot be used, we have to recover the number back. Then we get total saving of 69%. And when we do the same thing in the multiplication, we get almost 95% energy, because actually multiplications, when the number of bits increase, there is actually more than linear increase in the area power delay because of this squaring effect. And similarly here, previously the adders, the narrow adders were actually accurate. We can check with the SES adder is an approximate adder. There we can get much more savings. And yeah, this is the impact on the accuracy actually. So accuracy for the this is the percentage accuracy change. So here these are the results that there is actually for many cases this 12% may not be acceptable, but for some cases it's okay to accept within 10% error. There are some applications which are very error tolerant. And we have also done application study. So if for image sharpening application, if there is no soft error, then suppose this the PSNR values are 27, 27, 33, and SSIM values are this, right? But if there are 1% bit 1% 1 bit flips, or 2% 1 bit flips, or 4% 1 bit flips, then the numbers are here. So let us take just one sample example. Like for example, for DNN, in the, let us take this aggressive case, if there are 4% bit flips, so compared to 95% accuracy reduces to 82% for FTA and just 46% for EIF, and for VADF it reduces to almost same. It's not like too much decrease, maybe a less than 1 percentage point reduction in the accuracy. So that means for some image processing and some machine learning application we have tested the accuracy, and this is the same thing in terms of a graph. So conclude, we have proposed a novel approximate data format for storing approximate integer numbers, while also providing resilience to soft errors. Our VADF format offers rules for storing the operands into reduced bit weights, not just 32 to 16, but also 8, 12, 16, 24. Our format can compress data by various factors, and it offers a good amount of energy efficiency. So this is my research talk, and as actually Sumit asked, I will also share my research journey. There are actually what he mentioned is that what were the challenges you faced and how did you overcome that. So as I said, I hope it will be useful for some of you. So I did PhD from Oak Ridge and postdoc from PhD from Iowa State and my postdoc from Oak Ridge. So actually after coming to India, as we all know, I joined IIT Hyderabad, and joining a new college and a growing IIT, there are always some challenges in setting up the research. Sometimes you got funding, but there's no space to put your servers. So all these challenges come. So without making this talk negative, I will just share some of the things I tried. It's always not easy to speak about oneself, and I will not try to boast at all, but just share my humble steps I took to overcome those challenges. And then also this corona was a very difficult task, right, for all of us. So all the flow got broken. So what are the things we tried and which worked? So it's not easy to join a new college as a PhD. Many students understand the challenge. So it was not easy for me to recruit students for PhD. So what we did, we recruited interns during the summer and winter both. And the good thing was many of them were happy to work throughout the year. Some of them worked for 2-3 years, right? And there are some interns with me who joined, and after graduation they are still working. They are doing a job, and then they are also doing the internship. And this year they are applying for abroad. And there are some interns who have more than 10 papers with me. I have not seen their face because it's all Google meeting, right? So, and they are very self-driven, and there are some BTech, some of the good BTech students who did their final year BTech project with me, and then after graduation they are continuing the work, and some of the works they did at that time they are completing it and publishing it now. And I did have one MTech RA. So what you call MS, Master in Science, in IIT we call it MTech Research Assistantship, which is a 3-year program similar to MS. So he did very good work, and he got admitted to New York University. And many interns, as I said, who published research papers with me got admission at top universities, both in US and Europe, like University of Michigan, may not be Florida yet, but probably we'll try to connect to you and send our students there. Okay. And one of the interns, he worked during Corona, and he told me that there was a job interview of some US-based company. So in the interview, they asked about, okay, can you explain this paper to me? And he just explained it, and he got that job. So actually, the point is, many of the BTech students we have, like, of course, in IISc challenges are different. You don't have a BTech program, but they are simply interested in competitive programming and coding jobs. Even if they are from EC department, they want CS jobs, which is a little strange. But here, but what I'm trying to say that even with research, they can land in a very good jobs. It's not that research is only for PhD student. Research is for everyone. And on my part, I try to work with them, give them feedback on every line of the paper they write, every figure they draw. I try to help them and give feedback. So the writing is improving, their confidence, their motivation. So some of them, like I had a student who was from some for the lack of better term, maybe tier 2 or tier 3 college, and he got direct PhD admission at Northwestern University because he was very self-driven, and he declined a job offer to continue to publish research papers, and the researchers there, they found out his research papers and gave him job offers. Sorry, the PhD offers. And next very important thing is to collaborate with similar minded researchers. So I have done some collaborative work, like this one was with Professor Purvi in IIT Kanpur, also worked with professors at IIT Delhi and Guwahati. And actually it's also important to contribute to the ecosystem. See, the people we train, they may not join us, they may join someone else. But that is equally, I can take encouragement, okay, this is also part of my success. So I've given talks on how to write research papers, because many of the times we sit in committees of some students, their presentations lead to so much frustration that, okay, I thought let us at least teach them how to write research papers. So I gave that talk not only IIT Hyderabad but IIT Madras, IIT Roorkee, and so on. And then participated in faculty development program. And then there was a winter school on computer architecture, organized by IIT Bhilai and IIT Madras also. So our idea is that there will be some students who will, actually, like as Professor Prabhat Mishra just very nicely asked, that somebody became interested in a field is usually due to some good professor they contact. And if they fear some subject, it is usually probably it was not taught very well. So if we can actually, at least encourage them, and they like a course, most probably, if not now, sometime later, when they get fed with debugging jobs, they will think of a research career. And then we also have a very nice online MTech program, both in IIT Hyderabad and IIT Roorkee. So these are the students who are working in industry. And of course they have a lot of workload from industry, but some of them at least they are very also motivated for research work. And some of the one student he was in IIT Hyderabad when he was, that means I was in IIT Hyderabad and he was enrolled there in the online MTech program. And when I moved to IIT Roorkee, he has written a research paper with me. So, and there are some students who have joined for part-time PhD also. So actually the point is, especially in Indian academia, actually research, they think it's only a pie of PhD students. But we have to have a model, some kind of encouragement system where UG students are also encouraged, MTech students are also encouraged, and for interns also. For example, to call it bluntly, like in our promotion, they only count how many PhD students you have guided. That is at least one of the criteria. But we can also do a good work with interns or other BTech students, MTech students, and so on. Of course, PhD students are also welcome. So there should be a model or a way of encouragement of that also. Then one of my PhD student, he had very good industry experience, so he organized a Linux system administration hands-on session at IIT Hyderabad for multiple weeks together. It was a very intensive training program, and one of the BTech students from IIT who attended that course, he got a job offer from MS Azure. So actually these skills, one should never fail to learn the skill set. Because with ChatGPT, many companies are getting closed, many new opportunities are coming, and so you don't know which skill you learn, it gets useful. And even in promotion interviews, like I went through this associate professor promotion interview, they ask very, very basic questions. It's not they will not only ask about your research paper, they will ask whether you know the basics. And if you don't know the basic, they may reject you. It has happened, right? Somebody had a very good research profile, they did not get selected because they could not explain the basics. So one should not fail to grow their skill set, one should not ignore the basic courses, even with all the rush for research. And in-class teaching is very, very important. That is what I realized. So actually, this 2024, out of around 500 faculty members that we have in IIT Roorkee, I was shortlisted in the list of top 5 faculty members. I just missed. I was number 2. I could not get the award, but still it was in the good encouragement. And actually, I feel research is slightly easier to get good feedback from students. Is not that easy because they have different expectation. Sometimes you have taught a class size of 160. That is the largest class size we have taught. So it was one of those classes also where this feedback was found there. And these students, some of them, they got inspired. They took my course and joined for research project, either in the form of BTech project and so on. And they have either published papers or they're continuing to contribute to the ongoing projects. So yeah, as some of you know about me, that I have written close to 45 survey papers. So for that, I have read more than 5,000 papers in the field of systems, VLSI, electronics, plus 1,000 more in the field of AI, and I'm growing that still. So with the courses, you can never cover the emerging topics, and especially in the AI field, not only system but especially in the AI field, the growth is very, very fast. Like in AI, actually, if you read a paper which is more than 5 years old, actually probably you're not at the cutting edge. So especially during my postdoc and the early years of my faculty position at IIT Hyderabad, I used to read a lot. Now, of course, we have a lot of students. I don't get time to travel, teaching courses and giving feedback and so on, but still try. So, and these many students have told me that they have found these papers very, very useful. And not only that, they have helped me also. So, they have helped many young researchers to get into field, and also experienced researchers to stay updated. And some of these survey papers have actually predicted future trends like approximate computing. I have around 1,300 citations on that. And similarly, there was a paper I wrote on CPU, GPU, heterogeneous computing. So previously there was a debate. Intel published a paper. That GPUs are not too good. And there was a lot of debate whether it is CPU is good or GPU is good. But I motivated the concept that actually both have their own usage, and many of the supercomputers are designed using both CPU, GPU. So actually, through this, when you look at the history, you can predict the future. Then many of the even from industry we got a good feedback. And they actually also taught me to write good technique papers also. That means the novel technique papers. And so this is my last slide. It helped me generate novel ideas for writing research proposal, because once you have read so many papers, you are very thorough. You know what are all the works that had been done. You can compare your work with other works. You don't miss out key works, and then reviewer doesn't say that you have missed out the key work. So once you have done a very good study, you are very thorough. And also for consultancy projects, so that's like there people working in this. I'm working a consultancy project with TCS, so sometimes guide their researchers also. So that also helped me to guide them and give them good feedback. And now actually I'm a faculty member in EC and also a faculty member in School of AI. So I have a good now actually I'm doing more of AI, because I think although systems is important, but let's not make it our religion. It's okay to change your religion, right? Just because we did PhD system doesn't mean for the rest of the life we have to stay with system. We can explore. And through this course, through this study, I actually developed courses like advanced computer architecture for PG students, and computer architecture for AI, which is like the intersection of AI and computer architecture. So just two cents from me. Don't hesitate to embrace AI, as Professor Prabhat also said, that sometime you will find out a wonder through this. And of course, but actually many of those wonders will not happen if system were to not contribute, because this system, these AI models are so hungry. For example, you propose some model for traffic surveillance. A traffic police will never be able to deploy it without some system optimizations. So unless we make their power consumption low to make it happen within a battery power of budget, it will never be deployed in the real world, because how much data can they collect and how much data can they process. And one slightly subtle point, I realized that actually when I try to tell about my work, people don't get so enthusiastic when I tell about systems work. When we tell them, okay, we have designed a Gen AI model which can, or some AI model which can distinguish cat from dog, they think, wow. And when we say, okay, we have proposed a prefetching model, they say, what's that? How does it affect my life? So we need to actually make it a case to explain that, okay, without to laymen, to policymakers and all those, that system research is as crucial as AI, and without systems, a strong backing of systems, nothing practical is going to come apart from this fancy result. Like this last point, I'll say that Professor Sandeep Kundu, he told that the IT is consuming 8% of electricity, and 20 megawatt is a power, is the, you know, if ChatGPT is taking 20 megawatts for training, for that you require a nuclear power reactor, right? Just you have a supercomputer and you have a nuclear reactor side by side to it. So that's not feasible, and it will impact people's lives. So system research is as crucial. So we need to, you know, collaboratively take that risk, the risk or the effort for that. Okay, thank you so much for your kind attention.
Thanks first for the enlightening talk. Questions?
Yeah.
Hi, sir.
Okay.
3 questions. First is.
Actually, one question only. You can ask other questions during the lunch because we are a little late already. So.
How does 8-bit quantization compare with an 8-bit compression strategy in terms of the accuracy you get at the output? And
actually, when I say quantization, it's usually floating point to integer. Here it is integer to integer. So floating point has much higher dynamic range. So, for example, if you see IEEE 754 format with which is like single precision 32-bit, that is like it is 10 raised to power 38. That is the range it has. 10 raised to power 38, right? And here, if you have 32-bit number, it is only 2 raised to power 31. There's a huge difference, 2 raised to power 31 versus 10 raised to power 38. So, you know, bringing a 2 raised to power 31 number into 2 raised to power 7 is one thing, whereas bringing a 10 raised to power 38 number into this number is very different thing. So that is a different quantization in here. They both involve some kind of approximation, but the magnitudes are different. And usually when we say quantization, it's very specific to a neural network model, and that too in the inference stage. So you know some amount of, you know, information about the application already. Here it's like application agnostic.
Okay. Any more question?
Yeah.
Yeah. So you mentioned the range of values that RED, max RED and all that, right? So
Yeah. Max RED probably I showed here, or I just probably defined it. I did not include that number here. It probably is there in our paper. This max RED, it's not, probably here it's not there. Okay, here it's there. Just a minute, I'll present how to make it. Oops. Yeah, this max RED should be as low as possible. Yes, please.
Correct. So you can compute it for every value, right? Because you are looking at 32-bit values. So you can compute it and actually do that rather than sampling, like you said, about 1 million, you took some number of times.
Okay. Yeah. So you can always find out that. But the point is, out of the 10⁻⁶ numbers that we have generated, what was the worst case? We can always, for n equals to 32, we can always find out that from theoretical analysis itself without actually doing the simulation. But this max RED is for those 10⁶ random numbers that we have generated, which probably follow some distribution like uniform or Gaussian or something like that.
And I don't know whether you mentioned the approximate adder design.
No, that is not mentioned in this paper. That our previous work we have proposed this approximate adders.
Okay, let's thanks first once more.
Thank you.
The department is a small token.
Thank you so much.
Okay, so let's move for the next talk. Let's welcome Professor Venkat, Dr. Venkat Kalyan Tava, in bracket Kalyan. I think he likes his middle name more. He is an assistant professor in the Department of CSE, IIT Ropar. He is also an associate faculty of Center of Research for Energy Efficiency and Decarbonization. Earlier, he was a hardware performance architect in the Power System Performance Team, part of India System Development Lab, IBM India Private Limited, Bangalore. He is recipient of the 2022 Qualcomm Faculty Award for his research contributions to the area of memory and systems. He has 10 patents to his name and 18 publications in IEEE/ACM journals and conferences. Kalyan works in all the levels of memory hierarchy, that is cache, DRAM and SSD, in their redesign for performance and security. In addition, He works in high-performance graph analytics on GPUs. Kalyan received his PhD from IIT Madras. He is a member in IEEE and SCM. Over to you, and it is ready.
So, thank you for having me here and for the kind introduction.
It's read-only copy.
Actually, made some last minute changes. Okay. Good afternoon, everyone. I made the title "I Walk Down the Memory Lane" to make it a little more interesting, and I was planning to touch upon different levels of memory, give a high-level view of a couple of ideas that we have explored over the last couple of years. Right. Before we dive in, I'd like to take a moment to thank my parents and all the teachers I have had. It's with their blessings that I'm able to progress, and I also thank my better half for her continued support. Every person who's married understands the load they take, right? Now I'll quickly present the research overview of our team. Right. We work on both performance and security aspects at cache, DRAM, and SSD. Right. At cache, currently we are exploring ML-based prefetcher designs and data migration, data movement. Then on the security front, we are studying side channel attack defenses. At the DRAM, we are looking at ML-based memory controller policy design, which is adaptive to applications requirements. And then we also are exploring row hammer attack defenses. At the SSD, we are looking at the garbage collection design and DRAM cache utilization for the performance. And on the security, we are looking at ransomware attack defenses. Right. Along with that, we also are looking at heterogeneous memories, where we have a fast memory and slow memory. There, on the performance front, we are looking at how to deal with the page management. Then non-volatile memories, lifetime improvement, and the added flavor recently is the secure caches, right? And we also have works where we are exploring endurance attacks for non-volatile memories, right? I'm going to pick three among these problems. I'm going to quickly walk you through like what we have worked on, right? Here is the it's the Computer Architecture Special Interest Group. That's what we call ourselves, CASIG, at IIT Roper. We have handful of PhD scholars. They are the guys who have actually contributed, right? And so we are three faculty: Dr. Neeraj, myself, and Dr. Shishendu. He has moved to IIT Hyderabad recently, right? I'll skip the details in interest of time. To begin with, I'll start from the SSDs, right? And actually, I should thank Professor Prabhat. He has kind of given a gist of the approach that we took in his talk. So how many of you are familiar with the solid state drives? Okay. Fine. I thought you'll make my life easier. No. Okay. At least for SSDs, I have included few basic slides on to understand how it works and all. I'll quickly go through that, and then we'll hit the ransomware. Right. So the flash memory cell is basically a floating gate MOSFET. Right. We have the source and drain, and this is the conventional transistor. But in flash cell, we have a floating gate, right? And that adds a lot of new functionality to this. Meaning, when a very high voltage, or based on the doping, a very high voltage or very low voltage is applied to the gate, the electrons get trapped in the floating gate, right? Now, what it's called is tunneling. Now, what's the benefit of it? The benefit is the very next time when we want to switch on this particular transistor, its threshold voltage changes. Based on the number of electrons that are trapped, the threshold voltage changes, and we use that information to interpret what data the cell is storing. Okay, so that's why we have very quickly progressed from a single level cell to multi-level cell on the flash, right? Right. The interpretation can be right if when the standard threshold voltage is applied, if there is no current flow, we can interpret that as 0, otherwise we can interpret that as 1, right? In SSD terms, we have the floating gate state. If it is charged, we refer to that as programmed, and if there is no electrons trapped, then we call it erased state, right? Now, flash cell is non-volatile in nature, meaning that the electrons which are trapped in the floating gate will remain as is until reprogrammed, right, or until erased. Now, how do we read from this flash cell? Like I've mentioned, we apply the threshold voltage, and if there is current flow, we interpret it as 1 or 0 based on our understanding. And then how do we write to it? Let's say the cell is storing 1, then how do we, if you want to write a 0, how do we do it? Is we apply very high voltage at the gate so that all the electrons get repelled and fall back to the channel, right? And how do we erase? Sorry, I think the operation I mentioned was for erase. For the writes, we apply very high positive voltage where the electrons get trapped. If you want to erase, we apply very high negative voltage, right? And this is the erase operation. Now, unlike the regular SRAM and DRAM where we just have read and write, here we have an erase operation. So that's one of the key things, right? And this is one big constraint at the solid state drive, which is that before we want to write any new value, we need to erase the cell. It is called erase before write constraint, right? And because there is a physical movement of the electrons through the oxide layer, eventually there will be a lot of wear and tear, and it results in breakdown of the layer, and we will no longer be able to hold the electrons. So that's when we say that the cell has run out of its life. And flash has very limited endurance, right? The term we use is endurance, the number of times we can write or erase the cell. Okay. Now, this endurance was not a big issue for SRAM and DRAM for all practical purposes, right? But for most of the non-volatile memories, it is an issue, and when we look at the flash cells, it's a bigger issue. And like I mentioned earlier, based on the number of the volume of electrons that we are able to trap, we interpret different. We can interpret threshold voltages. So here we have 8 possible threshold voltages. So we can effectively interpret that as a 3-bit number, right? Here we have 2, and this is the single level, right? We have 4 bits, meaning we can distinguish 16 levels in the threshold voltage. That's the current trend, right? Now, the more the capacity, right, when we go from single to multi to ternary to quad, right, the density is increasing, but the speed of operation will be reducing because we need to try different thresholds in the steps and see at which threshold the transistor is switching on. So the operation is slower here. And the endurance, because of increased wear and tear, the ternary and quad cells run out fast, right? Now, that's the story of one particular flash cell. Now, just like any other memory, we arrange them in the 2 dimensions, right? here the terminology is slightly different. We have a string, we call a string where a column of flash cells are connected, right? We refer to that, and typically 32 to 64 cells will be connected. Then this is the minimum read granularity of the flash. And array is an entire is 2D arrangement. This is a collection of strings, and page is a row of cells, right? And the typical size of this page, it's not the OS page or the DRAM page, this is the flash page, okay? And the typical sizes would be 32K to 128K and beyond, right? And this is the minimum write granularity. So this is another fundamental difference when we move from SRAM, DRAM to the flash, where we can read as low as 4 to 8 bytes, but we can only write a page of data, right? There is a disparity between read and write. Then the 2D arrangement of such arrays will lead to what's called block, and typically a block can be of size 8 MB, and if we consider the page to be 128K cells, then there will be 512 pages in one block. And and this is one other important thing, that arrays granularity is now at block level. So reading we can do at bytes, writes we can do at page level, and arrays we can do at block level, right? And multiple such blocks will be stacked, and this is what we call plane, and multiple such planes would be placed in a die, and multiple such dies would be called what we call NAND chip, right? So this is what it would eventually look like, right? We progress from a simple flash cell to the NAND chip, right? Now these NAND chips can be ganged up together like this, and there can be multiple channels. Channel is an total independent communication. It's like you can say a private bus is connected to this set of NAND chips, right? And that's what we call channels. The number of channels we have, the more bandwidth we will have, right? And among the channels, the NAND chips are grouped into banks. Now, in low-end SSDs, we typically have 1 to 4 channels, but in enterprise SSDs, we can have much higher. And so it basically depends on the performance, power, and the overall size that we would require for our end application. So I'll skip the banks for now. So this is what a typical. Have you seen this? Huh? What about this? No. So this is the external SSD, and this is the internal SSD, which sits right nicely in on the motherboard. Both of them have the same internal structure, right? Now, just zoomed in. What we have discussed so far is one NAND chip. Okay, and now we are going to see the brain of it, which is the SSD controller. So to the host system, the NAND can be connected. There are many protocols that have been explored, right? It can be serial, ATA, or USB, right? And the main the SSD controller is the main guy who is who's kind of syncing up the requests and the data movement, right? So the SSD controller in general manages the NAND chips, manages the communication between the host and the NAND chips, right? And so what do you think the SSD controller would be primarily doing? It will receive the command from the host, right? Typically we are now talking about the secondary level, meaning that we would come to this only when there is typically a page fault, right? So the request would be, okay, get me a page of data starting from some address, right? So the NAND controller will take that, will divide that into all the things we saw, channels, blocks, planes, right? There can be dice also, and within that it needs to identify the page and then read from the NAND cells and send it to the host, right? This is a very primary job, but it has lot more things that it typically does. Let's quickly walk through them, right? It has reliability and maintenance features, it has security features, it has performance features to take care of, and other miscellaneous things that we just talked about. Okay, now if you look at the reliability and maintenance features, one of the functionality is address mapping, right? Then it needs to make sure that all the NAND cells are wearing out uniformly. We call that wear leveling, right? Then we have what's called garbage collection. So you remember that we cannot write to the same cell without erasing it. Now what is the problem there is, as such, it's a it will be a longer or slower operation, but on top of that the erase granularity is much higher, right? 8 MB or 16 MB. But what we wanted to do is we just wanted to write 4 kilobytes of page. Now erasing that huge memory block will be much more slower. So what we quickly do is we write it to a new location and we make note of it, right? That making note of it is what the address mapping, the FTL, does, where we have written, right? It's like when somebody wants to share their phone number, for example, or at that time for whatever reason you don't have your phone, you'll just find a piece of paper and write it, right? So that's what we'll do, but we need to make sure that it is made note of. And there is what's called over provisioning. Now you would have felt that you bought let's say 128 GB pen drive, right? Will you be able to use all the 128 GB? What is the visible size? Probably 104 GB only, but you paid for 128. Nobody is complaining. Yeah, so the remaining space is for what's called over provisioning feature, right? Whenever the some cells die out, the the SSD controller will go and start using these additional cells that it has.
Can you explain garbage collection with one more time? Garbage collection.
Okay, so we need to write a page of data. There is already a copy of it residing, but we cannot overwrite it. So we write it to a new location, right? Now what happens to this earlier data? We right now mark it as invalid only, right? In SRAM and DRAM probably we can just delete it also if you want to, but here what happens is we cannot delete it directly or erase it, because we need to erase a bigger block. It can be part of 511 other pages, right? We just right now mark it as invalid, but eventually there can be a position that most of the pages in the SSD would be invalid. So that's when the garbage collector kicks in, saying that okay, let me identify the blocks where majority of pages are invalid, right? All the valid pages will be moved from this let's call victim block to a new block, and then it will erase the victim block completely, right? That's the actual work of garbage collector, right? Then there are reliability features like read and program disturb and write abort. So the row hammer, what we are currently there is a lot of discussion about it, which is actually a read disturb. You go and try to read the same memory cell, DRAM cell, time and again, it's going to disturb the data in other, but that issue is there in SSDs since the beginning, right? And there is a write abort issue also, because now we are moving pages of data. What happens if there is a let's say power loss? So how do we retrieve the data, right? And ECC support is there.
I think you can just cut the part.
Cut. Oh, okay. Then there is something called smart. Basically it collects all the statistics and reports to the host whenever it requests, right? It's like it runs the diagnostics also. Then defect management, then it also supports right. All these are for reliability and maintenance. Now on the security front, right, we have an encryption and decryption engine in the SSD, right? Let me quickly go here. Where is that? Sorry. So here, this is a fingerprint reader, right? It's a safety protection that Samsung has brought up for their high-end SSDs. Now to support that feature also, the SSD controller will encrypt and decrypt the data, right? And only an authorized user can access it. Then we also have performance features where we have what's called disk cache. You are aware of disk cache, right? At the OS, whenever we are discussing about storage in the OS, they do talk about disk cache, right? But this is not that. And then the remaining interfacing. Now to manage all this, there is a dedicated RISC processor sitting inside your SSD controller. Okay. Now a quick high level view of what disk cache is. As the name says, it is cache for your NAND, because NAND is slower. And if you look at the access time, registers are the fastest, followed by L1, L2, L3, then DRAM, right? Then SSDs, followed by the magnetic disks, and eventually the tapes, right? And there's a huge gap between these two. That's why within the SSD there is a disk cache that is available. It is predominantly DRAM based, and some of the high-end SSDs do use SRAM based disk caches, and it's not new concept for SSDs. It was there even for enterprise conventional hard drives also, right? But in case of SSDs, it is helping us with one additional functionality, which is it is observing a lot of writes, right? And at the SSDs, we have issues with writes because it's going to eat up the lifetime, right? The maximum writes the disk cache is able to absorb, the longer your actual NAND will work, right? And if there is data available in the disk cache, it will speed up the operation, and also it will save a lot of power. Now disk cache will be caching the frequently used pages, the firmware, and any metadata that that you would require for your FTL management, garbage collection, etc. Right? And whenever there is a disk cache available, you need to supply give a battery backup to your SSD, so that whenever there is a power off, all the disk cache contents will be safely moved to the actual NAND. Right? Now with all that background of SSDs, now let's look at the problem, which is ransomware. Right? Ransomware, it's a malicious program, and as the name says, the attacker accesses all your data, encrypts them, and like the professor has showed in the morning, a nice pop-up comes onto the screen saying that you cannot access your data, pay so much, and all that. Right? Now over the years, the ransomware attacks have increased. I think this we have looked at somewhere in middle of 2024, right? So these are attacks in millions. Okay, and so with that as one of the problem, let's see what ransomware actually does. Okay, the operation. So there are different classes of ransomware, but if you look at a high level understanding, what we are saying it would do is it will read your data, encrypt that, and write it back. right? That's the basic operation. So it will read, let's say, a file A and write it back. Now will it write to the same location? Yes. Or it may not be, so it can write to some other location in some other directory, right? So that is the class B. Now the attackers have become much more sophisticated over the years, and they are spacing out these operations, okay, so that the defenses that are there on the system might not be able to detect them, right? Now our proposal Carder works for class A ransomware. For class B also we have tested, and we have found some limitations, and that's what we are currently working on, right? Let me quickly go through what we have observed. So here we have collected the traces of different ransomwares, right? The popular ones are the WannaCry, Rook, DarkSide, right? And we also run the standard applications, the standard encryption, compression, typical download, and disk fragmentation. These applications, we have collected the traces, and we observed how the overwrite ratio is, means how many pages were read and how many pages were written back to, right? And typically the ransomware applications, the overwrite ratio is quite high. And another point is the overwrite interval. Like I said, the attackers have become sophisticated. They are spacing out these operations. So there are some recent ransomwares which are delaying the read and write nearly by 30 seconds, right? Whatever the system is trying to notice, right? It needs to now widen up its window. And that's where we asked what can the DRAM cache can help us with, right? So we were looking at the number of requests the DRAM cache is observing over the time. Then we also looked at the number of dirty evictions that are happening from the DRAM cache to the NAND. And the third one is number of times the pages are getting overwritten in the DRAM cache, right? And here we have shown only for one benign and one ransomware to help distinguish that there is a clear, distinction on how pages are getting handled at the DRAM cache. So this is one observation that helped us work on this, where the title is DRAM cache assisted ransomware detection and recovery, right? And the features, how are we extracting them? I think I'll go to the next slide, that would help. So from the host system we get the request, right? We look at these requests. We are collecting some features. I'm going to give what those features are, right? This feature vector will be fed to the decision tree. Again, this was one of the models that Professor has touched in the morning, right? And based on the decision, we'll either say it would be ransomware or benign, right? So this will complete the operation. Now, one other critical point is how early we can detect it, right? So that's one point, and that was also one of the motivation for us to explore DRAM cache, because by the time requests come to the NAND, right, many of them get filtered, and many of the features that we wanted to observe would be even more spaced out, right? So the features that are used by Carder are, some of them are cache driven, the number of overwrites at the caches, number of dirty evictions from the cache, and from there we are looking at cumulative cache overwrites, meaning we would be observing in windows of 1 second and 10 seconds. So this cumulative is 10-second stats, right? And non-cache driven would be the number of erases, and again cumulative. Yes?
So you are monitoring the traffic to the SSD, is it?
Yes. And the erase length. So this also is an interesting parameter, right? Erase length is what is the size of data that you are trying to delete, basically, And for all the regular applications, the erase length is usually smaller when compared to ransomwares. So that is also one distinguishing feature. We have the accumulated one, and then accumulated over period of time also, right? So these were the primary features, and these are the secondary features that we have used. And so this, I think where is that? Oh, where is the sheet tree?
That slide is
Hidden, huh? Okay. Probably I'll just. Acha. Okay. Probably I'll just explain it here. So this is the addition that we have built, right? At various levels, we are looking at the features that we have collected to make a decision whether it is a benign or a ransomware application, right? And one second. Okay, I need to correct this. So the data recovery part. Now, again here, what the earlier disadvantage of SSD was now becomes our ally. Meaning earlier we were saying that it would be nice if I overwrite my current data, right? Just like I would do in SRAM and DRAM, but now I am writing it in a new location. Now for data recovery, if I carefully am able to track which all pages were overwritten in the past, let's say 10 seconds or 15 seconds window, right? And if I say, okay, now I have detected ransomware, I can roll back for the past 10-15 seconds, right? So for that we do quite a bit of bookkeeping here. And here too, if you are able to detect fast, the recovery queue size will be shorter. So with that, so SSD Insider plus was the best SSD based solution, which was detecting ransomware within 14 seconds, and with Carder we were able to do that in 11 seconds, right? And so here is the timeline on how early each of them is able to detect. See, for example, here we have I think Rook is better. So for each timestamp, both of them are collecting features and making a decision whether the running application is ransomware or not, right? And the faster we reach the probability of 1, the faster we are able to detect it, right? So in interest of time, I'll skip this. And this is the normalized queues length also, because we are able to detect faster when compared to SSD Insider plus we are able to reduce the queue size nearly by 40%.
What queue is
Yeah.
what queue?
Sorry.
What queue is
This is the recovery queue where we keep track of the changes of the past X time interval. So in conclusion, Carder is using the DRAM cache, and it is able to detect the ransomware early when compared to the current best solution, right? Now I'll just pause for a minute for any questions. Yes.
So when you say rollback, you can then recover the data as well.
Yes, recover the data over the past, let's say 10 or 15 seconds.
But during those 10 seconds, actually benign writes may also be happening. Are you assuming that the original application is running in malware for this ransomware?
So right now it's only one application at a time. Right. Because at the SSD process level information is not available, right? So. How much time do I have? 5 minutes. 5 minutes, okay. So one more step in the memory lane, which is DRAM, right? Don't worry, I'm not going to dive into basics of DRAM. I'm directly getting to the problem, which is row hammer, right? This work was done by a PhD scholar, Prasita, with my advisor, Professor Madhumutyam. I was collaborating with them, right? And this got published in ICPP last year. So here a ransomware attack, like I was telling earlier, if you time and again at a very high frequency access one DRAM cell, is going to disturb the cells nearby. And when we say nearby, how near? Is it the immediate row only, or 2 rows, 3 rows, what? That's what we call blast radius. Okay, and when row hammer was detected probably in 2012, 2013 time, the blast radius was just 1, meaning 1 row above, 1 row below were getting affected, but we are still scaling the DRAM cells, so they are getting more prone to this disturbance. Right now the blast radius is nearly 4, means 4 rows above and 4 rows below are getting affected, right? Now the threat model we have considered is the attacker knows the DRAM address mapping. It's even though it's hard to get it, but we can get it. There is a tool also that can help us to get the underlying address mapping. That will help the attacker to target the accesses. And the attacker has just user level privileges and is able to generate TRH's threshold on if we need X number of accesses within that 64 milliseconds of refresh time, right, to trigger a bit flip. That's what the threshold is, right? Now again, over the past 10 years that X has come down also. Right now we are looking at numbers which are within 3 digits, meaning within 1000 accesses itself we can induce a bit flip, not only to 1 row above and below, but 4 rows above and below. So for that, what we have proposed is cache line pinning. Again, there is no brainer. No, just from the name you can figure out what it is. What we are seeing is we'll observe the requests from applications at the memory controller, meaning basically we are looking at the LLC messes. And if we see that some requests are going to a few set of rows, we are going to pass that information to the LLC saying that you retain these cache blocks, don't evict them. That's why we call that pinning, right? And obviously we cannot retain many blocks, so there is a cap on how many we can retain. We have done some sensitivity analysis on that, but we figured out that even for a cache of let's say 8 MB, even if we are able to retain let's say 1024 blocks, that also is good enough, right? The steps involved are aggressive tracking, meaning which rows are getting targeted. Then here we have used an existing algorithm to keep the area overhead minimum. Then the mitigation is in 2 steps. One is pinning. The second is a fallback option to what's called migration, where the aggressor row is moved to an isolated location. Now I'll give a relatable example. Now when you were in your school, if you are making a lot of noise, what would your teacher tell you to do? Go and stand at the corner, right? That's what this migration is all about. It sees that the aggressor row is being targeted, it will move it to an isolated location so that even if it is getting accessed, it will not disturb anybody. So yeah, like I said, we are monitoring the cache requests at the memory controller, getting the information on which rows are being targeted, and when we are replying the data to the cache, we say that pin it in the cache. So that will not participate in the replacement till it is explicitly told to get evicted. Okay. So we have compared the CLP with the 2 state-of-the-art techniques, which are Aqua, which does the migration, and SRS is row swap. And now there is a problem with migration. What? It will disturb the class until that mischievous kid goes and stands there, right? The same thing here at the DRAM also. You are moving an entire page of data from X location to Y location. So during that time, the memory controller, or at least that rank, will be busy, right? So that is the problem with randomized row swap and Aqua also. And for benign applications, the performance is matching with Aqua, which is best. But for a 4-core run where we are running an row hammer attack program, we see a lot of benefit with CLP. by retaining the cache blocks of this attack program within the cache, we are reducing the traffic to the memory controller. So we are able to see a performance gain also, right? And the workloads are basically mixed of spec 2017 along with one rowhammer attack program. So any questions?
So may I request you to have this pause as a...
Sure, no problem.
We can have more discussions in the break.
Yes.
Because we are already running a little late. Questions?
Yeah.
So what is the overhead of the tracker that you are putting inside it?
Yes, so tracker we have used the Miras Grassy tracker, right? It is something like 4 to 10 kilobytes at the memory controller.
4 to 10 kilobytes
Kilobytes at the memory. We are basically tracking the aggressor rows. Yeah.
Okay. One more question. Okay. If there is no question, let's thank Kalyan once more. We have some momentum.
Thank you.
Okay, so since we are running little behind time and then there is one more additional activity, there is little change in the schedule. So the photographer told that there should be a group photo for all of us. So now we will all go to the CSA garden and take the group photo. Please don't waste time in chit chatting. So let's all go to the garden, then have the group photo. And then we will have the lunch. So people who are presenting the poster, please have the lunch initially, others please give them priority. As soon as you have the lunch, like whoever presenting the poster, come back and stand in front of your poster, and others also please try to help them giving feedback and then probably suggesting something. So maybe your next intern or PhD or postdocs are here, and who are presenting poster, probably your next employer is here, right? Okay. So let's break out and have the group photo. Thank you. And we will join back 2:20 p.m. sharp. Okay.
थोड़ा ऐड किया है सब तक इंस्पायर होकर।
हाँ नहीं